a note of caution to all the presenters. If the speaker gets a pop-up message in their screen saying attendee X is requesting a control, deny the request or simply ignore it. We request all the attendees to not to click on the request button at any point of time. Now over to you, Dr. S. Seetha.
Good morning and welcome to this first session of today. Today we have highlights from ISRO space science missions, the first interdisciplinary session, and we have two speakers in the first half and another two speakers in the second half. The first speaker today is Dipankar Bhattacharya. May I request LOC to put him on stage, please? Professor Dipankar Bhattacharya is the Dean, Core Academics Program at IUCAA, and he is also a distinguished professor at IUCAA Pune. His connection with Astrosat dates right from the beginnings of Astrosat when we were even preparing the proposals. He has, of course, contributed greatly to all the data related activities of Astrosat. He is our expert on coded mask design and coded mask analysis. He is at present the calibration scientist of the overall Astrosat, and he also chairs the Astrosat Science Working Group. With these few words, I now welcome Dipankar Bhattacharya to give the talk on science achievements from the Astrosat mission. Over to you, Dipankar.
Thank you very much, Seetha, for that generous introduction. And many thanks to the organizers for requesting me to present this science highlights of Astrosat mission. It's, of course, a great pleasure to do so. I will do this on behalf of the Science Working Group, which I chair, and of course, the entire Astrosat user community. So thank you all. Let me begin. So Astrosat, as Seetha said, is an Indian astronomical observatory which is based in space. It is a culmination of an effort spanning almost 2 decades. It started in 1996 in the conceptualization, and it was launched on 2015, 20th of September. So it has, a couple of months ago, it has completed 6 years in orbit. After the launch, there was an initial period where multiple payloads on board Astrosat were checked out one by one. Performance was verified, trial science was made, and full-fledged science operations began in April 2016. So in a few months, we will complete 6 years of full science operations as well. It's a large multi-institutional collaboration, of course, led by ISRO, and payloads and other elements contributed by several other institutions, most major among them being the Tata Institute of Fundamental Research, Indian Institute of Astrophysics, IUCAA, Physical Research Laboratory, Raman Research Institute, and our international partners, Canadian Space Agency and the University of Leicester. So Astrosat has a slew of instruments which covers a wide range of wavelengths that we can observe from space. What is shown here is on the horizontal axis is the logarithm of wavelength, and on the vertical axis, the atmospheric opacity. So as you can see, this is the visible part of the spectrum, which we can observe from ground because this penetrates the atmosphere and comes all the way to the ground, and so it is in radio. However, there are large ranges of wavelengths which cannot be observed from ground, and Astrosat covers a good deal of that part of the wavelength band, starting at the upper edge of the visible band, through ultraviolet, soft X-rays, middle X-rays, and all the way to soft gamma rays. So this is a huge range of wavelengths put together in one single mission which is actually quite a rarity in terms of space missions that are flying and have flown. So that is one of the key strengths of Astrosat. In addition to that, Astrosat has a very, very good timing resolution. So it can study fast varying phenomena. So it offers the most detailed study of intensity variation of sources across a large waveband with simultaneous spectroscopy, starting at about 2 electron volts all the way to 100 kilo electron volts. So it's almost about a factor of 5,000 in wavelength. Then we can do detailed imaging of nearby galaxies in ultraviolet bands. The ultraviolet imaging telescope is one of the most capable ultraviolet instruments ever flown, and that allows us to study star formation. Another very important aspect of Astrosat is that it records individual photon events. So that's the most versatile observing mode that one can have. So we can then combine these recordings in any way we like. We can filter any way we like, so that our desired science can be served in the best possible manner. Finally, it has the capability of measuring polarization in hard X-rays for very bright sources. This is an area which is completely pristine. It's never been done before, and in this wavelength band, the Astrosat is the first instrument which has the X-ray polarization measuring ability, flying in a space-based platform. So altogether, this turns out to be an excellent tool to study two specific classes of objects. One is newly born stars, which emit copiously in ultraviolet, and that can be studied very well with Astrosat. And remnants of stellar death, for example, compact stars like white dwarfs, neutron stars, and black holes, which produce high energy emission, X-rays, ultraviolet to X-rays, and also show extremely fast intensity variations. And Astrosat is very good in studying both these things. But this is not to say that it cannot study other things. I mean, Astrosat has the ability to study in huge range of objects and phenomena. And it is a community-driven observing program. So whatever the Astrosat users propose, and that's what gets observed. So we will see as we go along a whole range of different observing that has taken place with Astrosat. So to come to the satellite itself, it has these 4 different instruments which are co-aligned on the satellite deck. One is called the Large Area X-ray Proportional Counter, which has 3 units on the sides here. At the center, there are twin ultraviolet imaging telescopes. The ultraviolet imaging telescope in these 2 units covers 3 simultaneous bands, that is far ultraviolet, near ultraviolet, and visible. And in each band, there are individual filters, so you can also choose subband according to your science requirement. LAXPC has these 3 units, goes over the energy range of 3 to 80 kilo electron volts. At this corner, there is a cadmium zinc telluride imager, which has a detector which goes from 10 to about 250 kilo electron volts. And it has got a coded mask, and it can do limited imaging, timing, and spectroscopy. And this is the instrument which also gives us hard X-ray polarization measurement. On the side here is a soft X-ray telescope, which has got imaging optics, and it covers the range of 0.3 to 8 keV. It is able to do also line spectroscopy in X-rays. In addition to this, there is an instrument which is mounted perpendicular to all of these. This is a scanning sky monitor. It rotates and covers this hemisphere of the sky in a short amount of time to look for fast varying transient sources, which then, if anything is discovered, Astrosat main instruments can be alerted. So this satellite has been launched at an orbit which is at about 650 kilometers altitude from the surface of the Earth. Orbit is nearly circular and has a 6 degrees inclination with respect to the equator. So in LAXPC, the current situation is that one unit is operating optimally and another unit is operating with reduced functionality. One unit is off. In ultraviolet imaging telescope, of these 3 channels, near ultraviolet is currently unavailable. The other 2 are working. Okay, so just to give a quick glimpse of the spectral coverage and time resolution compared to some other missions which are plotted in the background, you can see that Astrosat has a very large wavelength coverage, of course, and also excellent timing resolution going down to 10 microseconds. So this is the strength that Astrosat has been exploiting in its science operations. So with this little introduction to the mission, let me go to the science that it has been carrying out, science observations that it has been carrying out. So as of today, there have been 2,404 individual pointings in different parts of the sky by Astrosat, and that altogether covers about 1,390 distinct targets. So many targets have been observed repeatedly as well, because in many cases we want to see changes in the appearance of a source over time. So this shows what is the observation that is currently going on. So as you can see, that covers almost all of the sky, except the near the equator, where there are some constraints, pointing constraints by the satellite. So plus or minus 6 degrees in declination is avoided for Astrosat pointing. The rest of the sky has been pretty uniformly covered by Astrosat pointings. The different types of astronomical sources that Astrosat has spent time on can be just broadly grouped in these various classes. By far, the largest amount of observing time has been spent on compact stars. It's not surprising because of its strengths. So this is white dwarf neutron stars and black holes. Then another significant chunk of time has been spent on active galaxies, where there is a supermassive black hole at the center, which accretes matter and produces fairly bright and fast varying phenomena. Then normal galaxies has taken a lot of time. Lots and lots of galaxies have been observed, particularly in ultraviolet, giving us excellent handle on star formation in these galaxies. Also, clusters of stars have been one of the prominent class of objects that Astrosat has been observing. Some amount of time has been spent on some specific fields looking very, very deep in ultraviolet, looking for faint sources, faint galaxies. Individual stars have been observed as well, supernova remnants, and then various other classes of objects which have taken small fractions of time. So let's now dive into the kind of results that one is seeing from the community in these various areas. I will sort of go from individual stars and then go up in scale to galaxies and clusters, and then come back to compact stars. So various types of observations have been carried out of individual stars. Some of the most interesting ones have been observations of giant X-ray flares from some of the stars. For example, this is one which is of Proxima Centauri, which is a star very close to us. Actually, this is the closest star to us which has a planet around it, other than the sun, of course. So here, this is the Astrosat observation, and this is HST, this is Chandra. And these observations show how the explosion or the flare energy moves from optical, starting in optical, into other wavelength bands, and that gives us some idea as to how these flares are occurring. Then similar flares have been observed also in other stars. For example, this one called EQ-PEG, where some of the brightest flares known in X-rays have been observed by Astrosat. The X-ray spectra of other hot bright stars have been obtained as well. For example, the Capella, HIP 23309, and some coronally active stars. For example, this fast spinning star FRCNC, you get a SXT spectrum, and from that you can measure the surface temperature as well as various other properties of the star. This particular panel shows an ultraviolet grating observation of a star called SU Lin. The nature of the star was in doubt, but with this ultraviolet grating observation and all these lines being identified, the star has been confirmed to be symbiotic because the spectrum resembles other symbiotic stars that are known. So these are some examples of individual star observations. Going to star clusters, there are lots and lots of cluster observations that have taken place. I'm just giving some highlights and samples. Of course, it is impossible to cover more than 200 papers that have already come out from Astrosat observations. So I'll just group them in classes and then show some specific examples, one or two. So star clusters are broadly classified into two categories. One is globular star clusters, where the distribution of stars is tight, compact clusters with highly dense environment of stars, and open star clusters, which are much more diffuse, but they're still gravitationally bound entity in these stars to each other. So in the globular star clusters, these are both VIT images, by the way, taken from Astrosat. So one can take the observation in multiple bands and then construct what's called a color magnitude diagram. So here you have the intensity or luminosity of the star on the vertical axis and color on the horizontal axis. The color means the ratio of the intensity observed in two different bands. So so color magnitude diagram, and usually stars classify themselves by falling into individual tracks in these color magnitude diagrams. This track shown in black where most of the stars reside. So this part is called the main sequence, and this is stars which have evolved from the main sequence and become giant stars over here. Now, of particular interest in these clusters are the stars which don't follow these major sequences. For example, here there are a bunch of stars which are called blue stragglers, because main sequence used to be there a long time ago. Then the main sequence stars have been depleted and they become giant, and this has become the main branch now. But some stars are still found over here. They are called blue stragglers. And then these stars, which are called horizontal branch stars or extreme horizontal branch stars. So properties of these stars are being studied intensely using the ultraviolet imaging telescope. And many clues have emerged regarding their properties, their companions, their origin, and their evolution. And one can see a whole lot of publications which have resulted from this. In open clusters as well, one finds these blue stragglers, and they are also of very particular interest. And the study of these blue stragglers with Astrosat has shown that many of these have companion stars. So the spectrum of the star cannot be represented by one star alone, but you have to add another component. And that component happens to be quite often extreme low mass white dwarfs. And this is very, very intriguing, because these extreme low mass white dwarfs require a binary history for formation. So this is now unraveling the evolutionary history of how these blue straggler stars came to be. And there are a bunch of publications where this has been and are still being investigated. Coming to diffuse interstellar gas. So there are regions in the interstellar space which get illuminated by bright sources or by shocks that are produced by fast movement of one parcel of gas through another. And they emit ultraviolet and other high energy radiation. And Astrosat has been successful in observing many of these. One class of objects which Astrosat has been surveying are called planetary nebulae, where newly formed white dwarfs illuminate the surroundings by ultraviolet photons emitted by its hot surface. And those then get re-emitted at various wavelengths, producing spectacular structures in the sky. And these planetary nebulae have been well known for a long time. And Astrosat ultraviolet observations have also shown beautiful pictures of these planetary nebulae. However, what Astrosat has discovered is some very large extended halos around these planetary nebulae. And it has been identified that these halos are coming from fluorescence from molecular hydrogen that resides around the planetary nebula. So this has been discovered for the first time by Astrosat, and it is not just in one object, but in several planetary nebulae which are favorably situated. These halos have been seen. In addition, it has also been able to observe emission arcs at some distance from the planetary nebulae, which are attributed to the gas that was emitted, the mass that was shed by the star before it became a planetary nebula. And even some streamers and jets have been observed from the planetary nebula. So these are all new discoveries which were not known before. In other larger regions, this is a remnant of a supernova. So a supernova sends the gas flying at high speeds of the order of tens of thousands of kilometers per second, and then they eventually slow down and move at tens to hundreds of kilometers per second when they're very large. And that's the stage that this very large supernova remnant Cygnus loop exists right now. And Astrosat has been surveying various parts of this Cygnus loop in multiple bands that Astrosat carries. And one example is, for example, this field where this little piece of this supernova remnant has been imaged in far ultraviolet and near ultraviolet, revealing tremendous detail about the ultraviolet emission and the filaments that exist there. And simultaneously, one can do the spectroscopy of this region with the soft X-ray telescope and identify what are the prominent emitting species. For example, magnesium and silicon are prominently emitting in these regions. So this is very interesting from the point of view of studying the supernova remnant physics as well as pre-supernova evolution, where all these elements have been synthesized. Now, going to galaxies, as I showed you, this is one of the very large chunk of observations that are being carried out. So, first I will talk about normal galaxies. So, one of the big projects that is going on with Astrosat is a survey of the Andromeda Galaxy. Andromeda Galaxy occupies a large region in the sky, and this is being covered by multiple individual pointings of Astrosat, and this is the image, a composite image that has been put together from these Astrosat observations in far ultraviolet. So from this galaxy survey, ultraviolet source catalog has been prepared, multicolor photometry has been done, which has led to the identification and classification of hot stars, and also the distribution of ultraviolet variable stars have also been carried out. And this is only the beginning of a long series of science follow-up that will happen from this input that has come from Astrosat. So this is the Milky Way. This is the Andromeda Galaxy, which is one of the neighboring galaxies, close by neighbors to us. But even the Milky Way has been observed with Astrosat, and the UV star counts from the Milky Way have been examined, the distribution looked at, and one has found that this has the stellar distribution in our own galaxy can be described by a combination of two disks. One is a thick disk and one is a thin disk. The thin disk with a scale height of about 300 parsecs, thick disk with a scale height of about 5 to 600 parsecs. So that's an interesting use of the ultraviolet observations that Astrosat has carried out. Now, one of the main objectives of observing galaxies in ultraviolet is to look at regions of new star formation, and this has been going on by various proposers and authors, covering a large number of galaxies. So star formation has been mapped and are being mapped in different types of galaxies. There are some examples here. This is the NGC 2336 is a spiral galaxy. You can see beautifully the spiral arms in Astrosat FUV image. This is Astrosat NUV image actually, near ultraviolet image. And using multiband observations in different ultraviolet bands, combining them with optical information, a lot has been learned about the distribution of star formation, the history of star formation in these galaxies. Here is one galaxy, for example, where this is a color diagram in FUV and FUV minus NUV, and you see a depletion in star formation near the center, and this is being attributed to possible hindrance caused by some active phenomena near the center of the galaxy, possibly by the central black hole that exists. So this is one area where there's a lot of activity that is going on with Astrosat. Now, those were galaxies which were sort of relatively field galaxies with fewer neighbors, but galaxies in groups and interacting galaxies and galaxies in clusters, as well as voids, are being studied as different classes. For example, here is an example of a set of galaxies in the Dorado group of galaxies, and star formation, how it is affected by the galactic environment in groups, clusters, voids, and so on, are being discerned from these observations. Here is an interesting example of jellyfish galaxies, where the galaxy is moving through the gas that exists in the group or the cluster, and that collision with that gas strips out gas from within the galaxy, and then these streamers, which result from this gas being stripped out, are also forming stars. So there are stars that are being formed not within the confines of the galaxy, but in the trailing streamers of gas. Here is a ultraviolet UVIT picture of a post-merger galaxy NGC 7252, where you can see these tidal tails, which are also bright in ultraviolet, and therefore there must be stars which are forming there. While these are in dense environments of galaxies, there are also efforts to look at the population of galaxies in relatively rare environment called voids. Here are examples of some galaxies that UVIT has detected in what is called a Bootes void, and the properties of these galaxies are also being studied with great interest using the ultraviolet observation that one has been able to get. Then coming to galaxies which are farther away, as I mentioned, there are certain areas in the sky which are being looked at for a very long time by Astrosat, UVIT, to look at very deep, to make very deep images and look at faint galaxies. And this has resulted in the discovery of very interesting types of galaxies. One example is this AUDF-S01, which is a Lyman-Leaker galaxy, a galaxy from which a copious amount of Lyman alpha photons are leaking out at a redshift of 1.42 or a distance of about 9.3 billion years. It is a region in the universe where no Lyman alpha leaking galaxy was known before. It sort of fills a gap in our understanding in the evolution of galaxies. So this is a very, very important observation. Coming to active galaxies, which are powered by central supermassive black holes, there are this central activity causes jets to be emanated from these black holes, from these galaxies in many cases. And if we are looking at the jet sort of coming towards us, then we see extremely bright emission, and which are also variable in short time scales. So such objects are called blazars. Many blazars are being observed with Astrosat. One example here is the OJ287, where using the Astrosat observations, very broadband spectroscopy is possible, and so all the way from ultraviolet to hard X-rays. The data have been put together to look at the spectral energy distribution, and this can be done as a function of time. So as you can see, the spectral energy distribution keeps changing its shape, and that's the interesting thing to study about these objects. So this monitoring broadband spectral energy distribution variability are being done for many, many such objects, which characterizes the evolution of emission region. And as you can see here, a very large number of authors have been engaged in such studies. Imaging of active galaxies can give you, in suitable cases, the distribution of hot gas, and that tells us how the star formation is occurring in these galaxies, and the role of the feedback from the active galactic nucleus on the process of star formation. And using ultraviolet spectra, one has been able to also discern the disk of accreting matter, how far away from the black hole are they truncated. And this galaxy IC4329A gave us a good evidence of a truncated accretion disk, which was inferred from UVIT observations. The timing of the emission from blazars, which you look at the intensity variations and then do a Fourier transform to get a power spectrum. And in some of these cases, the power spectrum, when they are created, they show a break in their slope. And this break is very important because this is related to the mass of the black hole. So one is able to estimate the central mass of the black hole, which is driving this blazar emission. So again, these are very interesting and important observations. Coming now to compact stars. As I said, these are remnants of stellar evolution. When the stars die, they leave objects of this kind, either white dwarfs, which are relatively less dense compared to the three. So it's one solar mass confined within about 10,000 kilometers radius, or an Earth-sized object with a sun-like mass. Neutron stars, a similar mass in about 10-kilometer radius, so it's a city-sized object with the mass of the sun. And black holes, which are extremely dense, so the mass distribution is actually not seen. It is enveloped by what is called an event horizon. So between these two,
Dipankar, you have 10 minutes, so 5 minutes to sum up and 5 minutes for questions.
Okay, thank you. So surface and magnetospheric emission in white dwarfs and neutron stars, all of them shine brightly when accreting matter from a donor or surroundings. Fast variability, outflows, flares, jets, these are common in these objects. So various types of observations have been done from compact stars. As I showed you, this is one of the major areas. For example, the Crab pulsar, it's a fast spinning, strongly magnetized isolated neutron stars. Pulses have been seen from Astrosat, and it has also been able to measure the polarization, hard X-ray polarization of the pulsar, which tells us where in the magnetosphere the emission originates from, and it's located in the wind zone. There's a white dwarf pulsar, which operates with a similar mechanism called AR-SCO, that has also been observed with Astrosat. However, what has been found is that there is the X-ray emission, pulsed X-ray emission is not detectable as yet, so the limits have been placed on it. In accreting neutron stars, we can classify them in two categories: high mass X-ray binaries, where magnetic field measurements have been possible from cyclotron lines. There are a number of sources for which cyclotron lines have been detected from Astrosat. So you usually have a spectrum like this, where there is a dip, which is in the cyclotron resonance scattering feature. That gives you a measure of the magnetic field through this relation. And particularly in one object, Hercules X1, the cyclotron line energy has been changing over the years. And with Astrosat observation combined with other observation, one has been able to find now in what manner it is changing. It has followed an initial decline, and it is now flattened out. For such objects, there are also other studies like timing, pulse detection, spin and orbital frequency measurements, quasi-periodic oscillations, continuum spectra, and so on have been done by a number of authors, and also a detection of highly ionized absorber around one of these sources called Hercules X1. Two ultraluminous X-ray pulsars have been observed, one in the Magellanic Bridge and one in the Milky Way, which also fall in this class. Of low mass X-ray binaries, we have rapid spectral and intensity variations, thermonuclear bursts, high frequency oscillations, etc. All of this has been studied with Astrosat. Burst oscillations, X-ray bursts, that is a thermonuclear burst on the neutron star surface, with coherent oscillations superimposed, have been seen in a couple of objects. Some very, very closely spaced bursts have been observed. Multiple bursts detected in several stars. And in accreting white dwarfs, super-soft phenomenon, for example, in VA3890 SGR, as well as some binaries in Magellanic Cloud has been observed. In accreting black holes is one of the major areas of study with Astrosat. They have highly variable X-ray emission. They produce quasi-periodic oscillations, broadband noise, Beck frequencies, etc. You can see This is a LAX-PC observation of one of the black hole sources. Here is 1915. SSM observation of the same. We have all kinds of intensity variations, as well as there are spectral state transitions. So this is broadband noise with break frequencies, and this spectral state transitions in a intensity spectral hardness diagram. The objects follow all kinds of weird patterns, and so these are different spectral states. The spectrotemporal behavior depends on the black hole mass and spin, accretion flow properties. So once you observe them, you can discern some of these things. Many of these sources are transients, and occasional large outbursts take place. So of the various types of observations have been done. These are some broadband noises which have been studied with propagation model, understanding the accretion flow around these objects. In some cases, these quasi-periodic oscillations have been seen. A large number of observations and a large number of papers have come out of the observations of this source. There are various other black hole sources which have been observed. So since I'm slightly short of time, I will not go to many details of this. One of the interesting things to note is that Astrosat has discovered the tightest correlation between the frequency of a quasi-periodic oscillation and the spectral slope of the X-ray emission. It also discovered a change in spectral state with coinciding with a giant radio flare, and using multi-wavelength observations with Astrosat SXT, LAX-PC, Chandra, and so on, it has been able to measure masses and spins of some black holes. Coming to the last topic, this is gamma ray bursts detected by Astrosat. We have so far about 500 gamma ray bursts have been detected, and of these, the favorably situated bright GRBs, Astrosat can measure polarization. And over the last 5 years, 20 such objects which have been identified, and measurements or confirmed upper limits have been placed on these objects. As you can see, some are actual detections and a few are upper limits. These are interesting because if you do time resolved spectropolarimetry, for example, you have a black body and power law, and power law as a spectral feature in 2 pulses of this gamma ray burst. And in polarization, you see low polarization here, high polarization there. So that allows us to understand what is the emission mechanism that is going on behind these objects. So to conclude, Astrosat has completed its original design life for 5 years, but it's still performing well. ISRO has committed continued mission support. A large number of targets have been observed with a wide variety of science goals. Much of the data, of course, is freely available from the archive. New observing proposals are being sought annually. The next deadline is 10th March this year. A target of opportunity observations can be proposed at any time. And these observations continue to make important advances in the area of hot stars, gas, ionizing radiation, nature of compact objects, mass flow around them, emission mechanism, gamma ray bursts, and various other things. So please do use Astrosat. Any help if you need, you can always contact us at the Astrosat Science Support Cell, which we run at IUCAA. Thank you very much.
Thank you, Dipankar, for the wonderful talk. And you covered the whole breadth of the results from Astrosat in a very, very comprehensive way. Thank you. I now request the attendees to please enter their questions on chat box, please. Questions? There is a question. what is the expected lifetime of Astrosat mission, and can we expect more astronomy missions like Astrosat in the future from ISRO?
Okay, so I guess both these questions I am not the best person to answer, but I will try. The design lifetime of Astrosat, as I mentioned, was 5 years, and that is already over. And but the mission is continuing to operate. Most systems are working fine. So as long as all the large fraction of the instruments continue to work fine, we have commitment from ISRO for support of this mission. So this could be another 5 years for all you know, or could be even longer. Many missions are in planning after Astrosat. So I hope someone at some point will give a roundup of that. So I don't have the time now to list all of them.
Yes, some more talks are there in the next, not IS2, but Interdisciplinary Session 3, I think, and no, Interdisciplinary Section 2, which is coming tomorrow or day after. And there are also future projected proposals in the other sessions of astronomy and astrophysics. Okay, there's one more comment. It will be good to hear the status of the instruments as well.
As I mentioned, most of the instruments are working fine. In LAX-PC, of the 3 units, 1 unit is working in full potential, 1 at reduced potential, and 1 is off. And in ultraviolet imaging telescope, NUV channel is not available. Other 2 are fine. Those are the only major issues with the instruments. With the scanning sky monitor, mainly 1 of the 3 units is now being operated in a standard manner. So these are the losses that have happened. Everything else is working fine.
Attendees can also raise their hands. So please raise your hands in case you have any questions.
There is a question from Shama. Can you just check the chat box?
Girish,
so Dipankar, there is a question in the...
Girish, go ahead and read it out.
Yeah,
so there are constraints on observing solar system objects. Are there any plans to do so as part of the overall scientific observations?
Yeah, so some comets have been observed actually. I don't have exactly the results of it, so that's why I didn't mention it here. But I know the comets have been observed, and I think we will hear the results soon.
So they are still analyzing, and first time they just missed it because they have to submit a proposal long before the actual application observations take place. But it is from PRL. I think we will be hearing about the result very soon.
Yeah.
So I have a question, Dipankar. So I'm interested in looking at the data on stellar superflares observed by Astrosat. Now I have not used Astrosat data earlier. So if I have to find out what observations exist for stellar superflares, is there an easy catalog, or do you have to sort of go through the full data and mine it myself to figure that out?
It cannot. No classification will exist that says that it is for stellar superflare. But if you want stars, that is possible. You can go through the quick list of sources, which there is a utility in Astrosat Science Support Cell called Astrosat Observation Finder. So if you name anything, a star or something like that, then you will get the list of observation IDs which have taken place, and then using that observation ID, you can go to the archive and find that data.
Okay. Thank you, Dipankar.
Yeah.
You can actually suggest Lalita Sairam's paper. So that may be a good starting point.
Yeah.
Yeah, that I already made a note of.
Recently, EQ-PEG, that's a very recent paper with Karmakar et al. That also is very interesting.
Okay, thanks.
And Jeevan has some data on this FRCNC.
Yeah. Okay, if there are no more questions, I don't see any raised hands nor in the chat box. Thank you very much, Dipankar. And we can now go on to the next talk. I request you to stop sharing.
Yeah. Thank you, Seetha, and thanks very much for listening.
The next talk is by Dr. Anil Bharadwaj. I now request LOC to put him on center stage, please. Dr. Anil Bharadwaj.
Then we are admitting him. He was in lobby. Okay.
I think Anil has just joined.
Yeah. Can you confirm Anil Bhardwaj has joined in the? He is there waiting in the lobby, I think.
It looks like there's a technical glitch at his end. We are admitting him, but he is not being able to join or something like this. Let us give us 1 minute.
He was there in the morning today
But
before the session started. So
right, he had signed in from a mobile phone, then he left. And he's trying to join now, but our end thing seems to be fine, so we're just waiting for him.
Okay, so should I tell him to join with the mobile itself?
I see that he's there. I see that he's in now. No, that's Aarti Bhardwaj.
No, he is waiting in the lobby. I can see that he is waiting in the lobby.
Oh, ma'am, actually, like means we are just trying to just admit him, but we are not able to just admit him. I don't know why. So like maybe like this
I
is
will contact
some
him. Just
issue with yeah, sure, ma'am, sure.
Some issues because all other participants who are admitting are able to join, but Anil is stuck due to some reason. He was there earlier. And his phone is busy too. Okay, looks like he was successful now. Yes, he's in. And he's a presenter now. So in principle, Anil,
I think yes, I got connected again now.
Great, thanks. This is much better. We can see you well.
Right.
Seetha, maybe you can start introducing Anil while he's setting up his presentation.
Is my voice clear now?
Yes, Anil, we can hear you loud and clear.
Great.
Seetha, are you there? Seetha? Seetha?
Yes, I can hear you. Can you hear me?
Yes. Can you please initiate the introduction for Anil while he's setting up? Anil?
Yes, I am doing it. I'm doing it. Yeah.
Anil, can you please present?
Yeah, Dr. Anil Bhardwaj, request you to also please start screen sharing. Dr.
Yes.
Anil Bhardwaj is the director of the Physical Research Laboratory at Ahmedabad. He was earlier the director of the Space Physics Laboratory at Vikram Sarabhai Space Center, where he initiated the planetary research activity. And he is the PI of the Menka payload on a Mars orbiter mission, and he is also the payload on the SARA. He is the PI of the SARA payload on Chandrayaan-1 mission. Over to you, Anil Bhardwaj.
Thank you, Dr. Seetha, and good morning, all the viewers and listeners live on this team as well as on YouTube. And thanks to SOC of National Space Science Symposium, the 21st of this series, for inviting me for this talk. I hope you can see my screen now.
Yes, we can see it in full screen mode. Yes.
Great, thank you. So I'm going to talk to you about Indian Planetary Exploration Program, particularly talking about the science results coming out from the Chandrayaan-2 and Mars orbiter mission. But I will also try to cover what has happened in the past with the Chandrayaan-1 as well as the upcoming missions. So I am from Physical Research Laboratory in Ahmedabad, which is celebrating now the 75 years of its establishment. And as you all know that as the country is celebrating its 75 years of independence, PRL, which got established in the year 1947 by Dr. Vikram Sarabhai, the father of Indian space program. So we are celebrating the 75 years of its foundation, and with the series of Vyakhyaans, which we call as PRL Kamrit Vyakhyaans. So all of you are requested to tune in on the YouTube channel of PRL. And Dr. Sarabhai, as you all know, has established PRL, not only PRL, he established many other institutes. And on the moon, we have a Sarabhai crater, which is on the near side of, as seen from the Earth, near side of the moon. And this crater is a big one. One can see it with a small telescope also. It is about 8 kilometer in diameter and about 1.7 kilometer deep. Now, talking about the Planetary Exploration Program, which started with the Chandrayaan-1 launch on 22nd of October in 2008. And after 16 days of travel, we reached the moon, carrying 11 experiments on board, as well as the Moon Impact Probe, which is the first Indian man-made object to land on the lunar surface. And it actually landed into the South Pole, very close to Shackleton crater, and at the desired location, which also proved a lot of technologies which is required in the future for India. So Moon Impact Probe is essentially the first man-made object from India to land on lunar surface, and it happened on 14th of November, and which is also the Children's Day. So it's a gift to the children of India from ISRO. Chandrayaan-1 has made a very significant contribution into the lunar exploration program, essentially discovering the hydroxyl and water molecules of lunar surface. Till that time, we are all thinking the moon is bone dry. It has not only looked at the surface, but also water ice deposits in the polar regions, particularly beneath the surface, looking at how the moon get formed, discovery of mini magnetospheres, various craters, volcanic activities, essentially talking about that moon is geologically active, as well as solar wind interactions with the moon, changing our scenarios, which all has come in more than 180 scientific publications. And if you look at this cartoon, which talks about how the solar wind interaction with the moon has changed from the simple scenario where we're all thinking the moon absorbs the solar wind as it comes from the sun, and we had a long wake or a plasma wake, but it is not true. And there'll be talk by Dhanya in PS3, which where she will trying to cover all these details. Many of the science results have come on the cover pages of various journals, including Science and GRL and things like that. But talking about some recent work which has happened in the last couple of years is looking at Grimaldi Basin in terms of looking at volcanism and tectonic activities, particularly using the Chandrayaan-1 data and combining it with LRO and KAGUA data, and looking at how this moon has been experiencing the volcanism in the recent past. And now the suggestion is that we see signatures of activities happening on the moon of almost like 10 million years or so in the recent years, so which suggests that moon is quite geologically active. And there is, of course, study of first of its kind, unrevealing the geology of an obscured ancient impact basin on the moon, which is essentially from the Cougar-Serrasil, and which is also using the Chandrayaan-1 data. So there's a lot of work which is still continuing happening with respect to understanding the composition of the moon and distinct unique features which has been thrown up by the Chandrayaan-1 mission. We are also looking at producing global maps of iron, magnesium, and calcium, combining the data of Chandrayaan-3 with the LPGRS, that is Lunar Prospector GRS and KAGUA GRS, to generate this kind of maps, as well as to look at the swirls, which are very bright features on the lunar surface. And they have, like this one, which you see, the Reiner-Gamma swirl. And they have very unique features that they are not only bright, but they're also sitting very close to or on the magnetic anomalies. And one of the ways to explain them is that probably there is a compaction of resulting cometary impact where the compaction happens, and the magnetic shielding is coming because of that, which is shown up as a bright features on the surface. So there's a lot of work going on in this area in terms of understanding the moon with the Chandrayaan-1. I'll be talking about Chandrayaan-2 subsequently. Now, coming to the Mars mission in the sequence, which we say MOM or Mars Orbiter mission, or we say that Indian MOM to Mars, which had the launch on 5th of November of the year 2013, and we reached the Mars after 10 months on September 24th of 2014, and since then we are in orbit around the Mars. It has been more than 7 years now, though the planned lifetime was just 6 months. There are 5 experiments on board carrying a weight of only 13 kgs, whereas the total mass of the spacecraft is 1300 kgs. And they are all situated at different locations on the spacecraft, depending upon their scientific objectives. We have now got a very large number of full disk images of the Mars, looking at from different seasons and things like that. But using MCC now, we can get surfacial features as well as information about the dust and clouds situated on the surface of the Mars, above the surface. So MCC in the RGB can actually be used now to look at not only just the surfacial features, but also processes happening above the surface. There are many more information which has come out, like looking at Phobos passing in the front of the Mars, or looking at Valles of Marinus, which is actually one of the biggest canyon in our solar system. And you see it completely filled with the dust and clouds now, but some other times you don't see at all, and you can very clearly see the whole canyon, in fact. But good information about the flow patterns, like Mangla Valley is seen over here, where you see these features which very clearly shows the flow of flow features actually, And they have now been interpreted in a very different ways compared to what we were thinking earlier. Or one can think about ice clouds in the Mars getting orographically generated. Basically, in the leeward side of this mountains, you see this white patches, which is actually not the superficial features, but clouds sitting in the surface and the atmosphere of the Mars. And you see them in the global pattern, which you're seeing over here in this one, or even in the regional patterns. We have now seen, in fact, sphere albedo. Basically, the whole Mars is now having a global albedo at 1.6 micron, which is obtained from MSM on the Mars Orbiter mission. And we have got good information about Phobos and Deimos, actually, the two small natural satellites of Mars. And this all is possible because of the highly elliptical orbit of the MOM around the Mars. In recent years, now we are looking at also Pittel crater, for example, using MCC images from the MOM mission, which now talks about that this is consisting of pits and chains of pits as well as cantina. And this has revealed, in fact, that there's a wide opening occurring at around 2.6 billion years ago. And this is one of the youngest and largest collapse structures on the Valles of Marineris on the surface of the Mars. So a lot of new information is now coming, still continuing by analyzing the data from the MOM mission. And talking about the science of the Manka, which has now given us a lot of new information about what is happening on the evening time exosphere of Mars, looking at the distribution of dominant gases like carbon dioxide, nitrogen and carbon monoxide and oxygen, and their distribution at an altitude of somewhere around 260 to 375 kilometers. And this is actually the first in situ measurement of the evening time of the dust side atmosphere of or exosphere of the Mars. And it shows a significant orbit-to-orbit variabilities, and one can use that to actually find out where the carbon dioxide dominated atmosphere changes to oxygen dominated atmosphere. And what is observed is that this happens at an altitude of somewhere around 260 kilometers for the evening sector or in the dust side, whereas in the subsolar regions, this happens almost like 20 to 40 kilometers above, and which is a huge change because that has serious implications on many processes, particularly the dynamics and thermodynamics of the atmosphere of the Mars. Another new result which has come out from the Manka is the discovery of hot argon on the Mars. Essentially, if you look at the distribution of argon, we see it increases as we come closer to the Mars with the MOM going in elliptical orbit. But we do see a significant change in the profiles, essentially the temperature of the argon. And at times we see argon, which is almost like 150 Kelvin temperature higher than the ambient argons, which in turn suggests that these are suprathermal atoms. And these have significant impacts because they constrain the models of energy budget as well as escape processes. And this has been used now by NGIM's instrument on MAVEN to further show the presence of argon. So this is essentially a substantiation of what has been seen by a Manka instrument on the MOM, that MAVEN mission also has seen this hot argon. And the process probably is that these are collisional interaction between non-thermal oxygen, which comes from dissociative recombination of O2, and which actually hits this argon and provides them the energy. So these are important information which is coming out in terms of understanding the atmospheric escape processes, as well as to understand the sputtering which is happening in the atmosphere of the Mars, not on the surface. During June 2018, we had a planet encircling dust storm event, which is called PEDE event. And luckily, MAVEN was on the morning side and the MOM was on the evening side. And this unique combination of the two spacecraft around the Mars has now been used to look at the distribution of argon. And it is shown that there is a down dust asymmetry existing in the abundances of this argon, as you see here in the red and blue lines. The red is for the MAVEN observations from the dawn side, that is the morning side, and the blue is dusk side or the evening side. So this is a new result which has come out by combining the two observations from the two missions. And this is actually also essential because now we can combine the data sets from different missions to understand what is happening globally on the Mars. And this has been actually followed up to understand what happens in the ionosphere, particularly looking during this dust storm periods, because MAVEN has instruments which can provide information on the ionosphere of the Mars using the LP, ROSE, and GIMS, and which has been coupled with photochemical models. So now we are looking at the Mars in a comprehensive way, where we look at the observations from various missions and combining it with the photochemical models. Another way in which MOM mission of India has now been used is to study the corona of the sun. Now, this is done using a technique called radio occultation technique, which happened in May and June of 2015, when the Mars and Earth was on the opposite side of the sun, and the radio signals coming from the MOM passes through the corona of the sun. And one can use this to actually look at the turbulences. So this was a unique way in which we use the downlink S-band frequencies obtained at IDSN 32-meter antenna in Bangalore, and the MOM oscillator as well as the delta DR on the surface on the IDSN. So this was done in a closed loop way, and with a Doppler frequency of 1 Hertz. There were 9 observations which have been carried out during this period, which has provided us very new information about the solar corona. And if you look at the turbulences which has been obtained by analyzing the data for the sun at 4 solar radii to 20 solar radii, the spectrum changes. And if you combine this information to look at what happens as a function of solar radii on the x-axis and spectral index, which is basically a signature of turbulence on the y-axis, you see that the spectrum changes drastically as you crosses about 10 solar radii, which in turn suggests that between 0.2 to 0.4 solar radii, which below 10 solar radii, you have a spectral index of 0.2 to 0.4, which in turn is the region where the solar wind is actually accelerating. And beyond about 10 solar radii, you get a 2/3 fall, which is more or less similar to a Kolmogorov type of turbulence spectrum. And if you combine this information with respect to what has been obtained in the previous observations, like Ulysses or Galileo, we now know that during very low solar activity of 2015 May-June period, the spectrum index has a drastical change with respect to what is seen in the high solar activity period. So this is providing you new insight into peculiar Fable maxima of the solar cycle 24. So Mangalyaan, as you all know, is the first Indian interplanetary mission. It made ISRO the 4th agency to put a mission around the Mars, the first Asian country to reach the orbit of the Mars, but the first country in the world to have the successful insertion of orbiter around the Mars in the first attempt. And of course, we all know that MOM is, of course, the cheapest mission so far. It has crossed the Earth sphere of influence and orbiting. And it is the first Indian spacecraft to have the full-scale onboard autonomy, and which has now been demonstrated equitably well over the last 7 years or so. And it is, of course, the mission which has crossed Van Allen belt, which is basically the radiation belts 39 times. So it has got a lot of applause from not only the country, but outside the country also. And Government of India, realizing its uniqueness in terms of technological feat, has put the Mangalyaan on the back of 2,000 rupees note. So I hope all of you must have seen it. And this is essentially to say that this is a major feat in terms of technological development within the country. Now, moving on to the Chandrayaan-2 mission, which is a much more complex and complicated mission than the Chandrayaan-1, because it not only had a lander, orbiter, but also had a lander and a rover. And we know very well that after the launch on 22nd of July of 2019, We went into orbit around the Earth, essentially increasing the velocity so that we can reach the moon. This is a very optimum way of utilizing the fuels on the spacecraft to have this kind of trajectory. We went into the lunar transfer trajectory on 14th of August and got inserted in lunar orbit on 20th of August of the year 2019. And then we had a planned landing on 7th September early morning, and we all know what happened. But the orbiter is in orbit around the moon in 100-kilometer circular polar orbit. And there are 8 experiments on board on the orbiter, which are functioning very well. They are terrain mapping camera 2, XSM, IIRS, CLASS, LN, S-band SAR, CHASE-2, and DFRS. And they are looking at the moon in a much greater detail, looking at mineralogy, water composition, distribution, elemental composition, looking at lunar exosphere, or looking at subsurface features and the plasma composition very close to the moon. If you look at how this Chandrayaan-2 orbiter is looking at the moon in different wavelengths, we have visible and IR region, we have terrain mapping camera 2, IIRS, that is infrared imaging radio science experiment, then OHRC, which is optical high resolution camera. In the X-ray regime, we have CLASS and XSM. CLASS is looking towards the moon, and XSM is looking towards the sun. We have active sensing happening in the radio regime using dual frequency SAR, LNS band, and dual frequency radio science experiment, and in situ measurements happening with the CHASE-2. So if you look at this from microwave to almost gamma rays, X-rays, we are looking using the Chandrayaan-2 orbiter. Terrain mapping camera 2, some of the results now I'm going to discuss in very brief, which is basically a 3-view camera, where you get 4 nadir and aft, and combine that, you can generate the DEMS and then as well as the ortho images, which has been shown here for the Sarabhai crater, where you see how does it look like as you see, as well as the DEMs or digital elevation maps of the Sarabhai craters. And one can also get a good view of Lindbergh craters, which is a 3D view generated using the Chandrayaan-2. New science results is talking about lunar crystal shortening, which is a phenomena which is happening on the moon, and where we try to look at lunar wrinkle ridges, trying to estimate the crystal shortening and determining when it actually happened in the past. And this is one of the examples which is looking at how this wrinkles are actually globally shrinking the moon and its surface. We have also looked at stress and strain, which also comes from different features on the surface using terrain mapping camera 2 on the Chandrayaan-2. And this is basically looking at the interplay between the global contraction stresses and the basin-related tectonic stress regime. So you look at the features on the lunar surface and try to estimate how much is the stress undergone by different features. And also to look at mare regions, which are basically believed to be the oceans, now getting filled up due to various processes happening. These are 2 examples of a Brax crater as well as Hoffman crater, where we see that almost like 40 and 70% of this mare features have been filled already. And this suggests the movement of the material which is happening on the lunar surface. As well as we are looking at now mass wasting on the moon, essentially looking at various features or boulders which are situated at the inclined locations and faults, and to understand their dominant roles in triggering mechanism, which is not well understood. And this all is coming with help of the Chandrayaan-2 mission. L-band and S-band SAR, dual frequency SAR instrument, is now looking at polar regions, particularly beneath the surface, to look at features. And this also is being now used to estimate the water content. And using OHRC, which is of course the highest resolution camera available on the Chandrayaan-2, one can now get features as close as 25 centimeters on the lunar surface. So OHRC is now giving us unprecedented spatial resolution on the lunar surface. IIRS, as we all know, now has amply demonstrated the water presence, which has been discovered by the Chandrayaan-1. So Chandrayaan-2 is following up on that in terms of making us understand better as well as to look at how the distribution of the water is over the surface. So you see here the various steps of the IIRS, which provides you information about the total water content. And one can see that it varies to almost like 800 ppm levels. And you can do this by looking at various steps at different geological locations like plagioclast regions, or as well as low and high calcium pyroxene regions. And the different features which is coming from IIRS is now being used to understand the mineralogy as well as the water distribution. One can do this in this, which you see here is a composite picture where you combine this information from IIRS at different bands to come out with temperature distribution of the surface as well as the water distribution, which is shown in D and E over here. So IIRS is now adding up information on the distribution of water as well as temperature distribution. And one can also use it in different ways to look at various features, or one can say that one moon in many colors, where you get this information about the water distribution, temperature distribution, and mineralogical distributions. The class instrument, which is exospectrometer on the Chandrayaan-2, has now seen all major elements on the lunar surface: magnesium, aluminum, silicon, calcium, iron. But it has also seen sodium, chromium, and manganese, which has been very clearly seen, particularly when you have a large flare on the sun. And this is now being used to understand the magnesium distribution, for example, where you see how the magnesium is distributed, or to look at it with respect to magnesium to aluminum ratios and compare them with what is seen by the Apollo and Luna missions, basically from the return samples which have been brought by them, and how does that compare with what is seen with the Chandrayaan-2. Chromium magnesium, as I just mentioned, is now being compared with respect to what is seen by the Apollo sample returns. And there are unique features now seen by the class, particularly when the moon is going around the Earth and passing through the mangrove tail, which happens every 27, 28 days. There is a bust which is seen in the signature of on the spectrometer, which is quite likely because of the tens of keVs of electrons present in the mangrove tail. And it happens as a very short bust, somewhere around 6 hours plus minus of the full moon. And it is varying from different crossings, as you see over here. So there is no fixed pattern of that. And it is found to increase over the last 2 years, which essentially probably is suggesting about the increase in the solar activity, linking to the changes in the magnetosphere of the Earth. But there are features which are seen in the non-geotail particle events also. So there's a lot of things which is to be understood now to understand what is happening on the class instrument. A class is now being used along with the Chandrayaan-1. That is the Chandrayaan-1, Chandrayaan-2 data has been combined to come out with the global maps of the magnesium, elemental or aluminum and silicon, and to compare them between class as well as the M-cube on the Chandrayaan-1. So this work has started now, where we are trying to combine this because they are at different spatial resolutions. So one can get a good information if you combine the class observations with M-cube data. So this is what you're seeing here, the global maps of magnesium and aluminum now being generated by combining the M-cube on Chandrayaan-1 and class on the Chandrayaan-2 data. Talking about the solar X-ray, 5 minutes. Okay. Solar X-ray monitor on Chandrayaan-1. This is one of the most sensitive solar X-ray monitor on board, providing resolutions and accuracies as sensitivity, almost like 2 order of magnitude better than the GOES, and therefore it is able to see a very large number of sub-A class flares. It not only look at the whole data, but it provides you the spectrum in 1 to 15 keV band every 1 second. And since its operation in September of 2019, it has been providing very good information about the solar XF in the 1 to 15 keV band. And as you see here that as the spectrum or the class of the flare changes from A to X, how does the XSM looks at this spectrum and provides you the spectral coverages. One can get this information both from PRL website as well as from Pradhan in ISSDC. And there are large number of science results which has come out from this exam, where we talk about not only just very large number of sub-A class flares, more than 100 now, particularly happening from the quiet region of the sun, but also the first measurement of the abundances of the low first annihilation potential elements on the quiet sun, essentially. And you see here the abundances of magnesium, aluminum, silicon, which have now been looked up, particularly in the very small flares also. And this provides you information about the new things which is happening, particularly in the deep solar minima of 2019, which is, of course, the lowest solar minima in the last 100 years. New results are also pouring in, talking about the studies of compact flare producing CMEs via magnetic arcade blowout. So you will see this in paper in Joshi et al., Bhuvan Joshi in NSS. Soft X-ray spectral diagnostics of the multithermal plasma and the solar flares. Mithun et al. Is going to talk about that. And investigating the heating of quiet sun in DAM analysis, combining the data from XSM and AI. And Mandal et al. Is going to talk about that. Talking about the CHASE instrument, which has now a good coverage of what is happening in terms of distribution of gases in the exosphere of the moon. This is the plot which shows about the diurnal variation of argon. This is the first global observation of argon-40 distribution in the lunar exosphere. And here it compares it with what has been seen by the LACE and Apollo time frame. But in the mid-latitude, this is the first observation of its kind, because there is no observations of argon-40 in the mid-latitude. And if you combine these observations with respect to the distribution latitude and longitudinally, it shows you enhancements over creep region, but also in the South Pole Aitken Basin. And this is now being trying to explore that why this kind of anomaly is seen in argon-40 distribution, whether it is to do with the surface exosphere interactions, or it is some unknown processes which is happening, which is giving you anomaly features in the argon distribution over the lunar surface. And one can tune it to a talk of Dhania in the PS3 section for more details into this. We are also using this to look at what is happening with the ground-based observations. So this is an attempt now being made using EM polarimetric observations of Renal gamma to look at the polarimetric features which will give you information about the grain sizes and roughness, which is very important to us for us to understand these features of sorrels and like Renal gamma. What next? We are now working towards the Chandrayaan-3 mission, which is going to happen this year, which is going to be lander and a rover mission. And this will have 3 instruments on the lander and 2 instruments on the rover. These are all going to be flown on the lunar mission for the first time. And Chaste is going to give you information about the distribution of the temperature beneath the surface of the moon, almost like 10 centimeter below. And the APXS is going to provide you elemental composition of the lunar surface, providing you in situ measurements at very small scales of resolution in terms of its distribution on the surface. And that is why this is going to be a ground truth observations compared to what we are seeing from the orbiter. In the future, we are also looking at an ISRO JAXA mission, which is going to be a polar mission, where we are planning to have a launcher and a rover from the JAXA, that is Japan, and ISRO is providing the lander. And there'll be instruments on the rover, which will be contributed by both Indian and Japanese science teams. And this is expected to happen in 2024 or 25 time frame, where the idea is to actually look at the permanently shadowed regions also, which is, of course, most important and interesting to understand. In very near future, we are also talking about the first Indian mission to Venus, essentially because Venus is less explored so far, one of the inner planet compared to Earth towards the sun. And it is also very unique because it has a surface temperature of about 800 Kelvin and pressure of about 90 bar. So it is very, very different compared to Mars. And it has very unique features like what you see over here. The Venus is that it is full of clouds. You're not seeing the surface, you're seeing actually the clouds, which are situated at an altitude of somewhere around 40 to 60 kilometers above the surface, where the pressure and temperatures are quite benign. It is very similar to that on the surface of the Earth. So there are a lot of scientific and interesting unknowns which need to be explored in the case of Venus, which rotates also very slow. It takes about 120 days day and 120 days night on the Venus compared to 24 hours on Mars or Earth. And therefore, Venus is having features which are very unique, very distinct compared to any other planet in our solar system. And being closer to the sun compared to Earth, it receives much more sunlight. So almost like a factor of 4. And therefore, you are seeing features which are very different than what we can see in case of Earth. So India is now planning to have a mission to Venus, where we are interested to look not only at the surface, but also in the atmosphere and the interaction of the solar wind with the Venus. And this is going to happen very soon. We are working on to this mission. In addition to this, we are also talking about a mission to Mars, that is the MOM-2 mission, where the idea is not only just to send a orbiter like the MOM mission, but to also think about landing on the Mars. So this mission is also in progress in terms of discussion and understanding of how we can do that, as well as the capability which is required to have the technological requirement which is required for having a landing mission on the Mars. So thank you all for listening patiently to this, and I would like to thank all my colleagues and collaborators on the Chandrayaan-1, the Mars rover mission, and Chandrayaan-2, and of course the upcoming mission in collaborating in a big way. And thank you all for listening patiently. Thank you. Dhanyavad.
Thank you, Dr. Anil Bhardwaj, for the extremely illuminating talk. And while we are waiting for the questions on the chat box, if there are people who are raising hands, please let us know. Dr. Bharadwaj, with the IIRS and the dual frequency synthetic aperture radar, will we get better estimates of the amount of water on or under the surface of the moon?
Yes, certainly, because IIRS is going to provide this information over the surface, and LNS bands are beneath the surface. The only issue is that LNS bands will not be able to give you global coverages, because it is it has a very large power requirement and it's largely operating in the polar regions. Whereas IIRS on the other side is a passive spectrometer, so it needs sunlight, to shine up the surface to get information. So, but there are regions where you will get complementary information both over the surface and beneath the surface, combining these two instruments.
There is one more question. I think they have missed some points in your talk. What are the objectives of Chandrayaan-3 mission, and how is it going to be different from Chandrayaan-2?
Chandrayaan-3, as you all know, as I mentioned, is not an orbiter. It is lander and a rover. So lander is landing in the polar regions, and then the rover will come out, and rover will move onto the lunar surface. It is expected that it may travel to almost like a kilometer around the landing site, because it needs connectivity with respect to communication also. And so it is going to be more or less, you can say, in situ measurement on the lander and rover. Whereas on the Chandrayaan-2, we have an orbiter now, which is in orbit around the moon, providing you remote sensing data. So it is going to be a good combination where you look at the global image of any object on the surface and combine it with the in situ measurements. For example, if you look at the elemental composition, which is going to come from the APXS or from LIBS, and combining with what we are seeing from class instrument, for example, or looking at the mineralogy, which is coming out from IIRS. So it is going to be a complementary but unique in its own way, because of in situ measurements done by the experiments on the rover and the lander. And as I just mentioned that the Chandrayaan-3 has a CHASP instrument, which is going to give information about the temperature distribution beneath the surface. And this is going to be very important because we all know that the moon regolith is highly non-conductive. So how the heat is transferred, inside from the surface is going to be a big challenge for us, all of us, to understand. And this is going to be a unique information when we look at the temperature profiles beneath the surface using the chaste, which is going to go down almost like 10 centimeter beneath the surface.
Thank you, Dr. Anil Bhardwaj again. And please look into the chat box in case there are more questions. We are already running 6 minutes late. I now hand it over to Dr. Tarun Pant, the chair of the next session. Thank you. Thank you, Dr. Anil.
Thank you. Thank you very much.
Thank you, Dr. Seetha. Thank you very much. Dr. Anil, it was a fantastic talk. Now we have come to the third interdisciplinary session, that is session 3 on remote sensing and meteorology from space. And we have two very eminent scientists who will be giving talks in this particular session. Very interesting talks are lined up. So on my behalf and on behalf of Dr. D. Jagadheesha from ISRO headquarters, my co-chair, we welcome the speakers and welcome you all to this session. As you all know that from this morning's presentations, it is amply clear that why remote sensing is so important, because it not only gives us where we are today and where we are going to go in terms of our place in the universe, as the first presentation showed today, and then the latest discoveries from the different planetary systems, including our own moon. So remote sensing and meteorology of our own planet, Earth, it's very important. So without further ado, I would like to invite our first speaker for today, Dr. Ahmed Patra. A brief introduction to those, especially for our young generation, because he doesn't need an introduction to the people who are already in the field, but then the young persons, young researchers, I think it would be inspiring. So I would just give a brief introduction. Dr. Ahmed Patra is a very eminent scientist, eminent ionospheric scientist, and also a science administrator now. He is at the helm of affairs as director NARL, National Atmospheric Research Laboratory. His research interests had been as I said, atmospheric ionospheric physics, especially plasma irregularities. He is known as the 150-kilometer eco person, okay, because he has shown us that these 150-kilometer ecos could be observed over Indian longitudes using our own radar. He's a member of Indian National Science Academy, Indian Academy of Sciences. He's a fellow of both the academies. He has received a PRL award for his eminent contribution in the field. He's a member of various committees and advisory boards of ISRO and other institutions in India. For instance, he's a member of the Apex Science Board of ISRO, and then he's also in the as a member representing India in joint national committees for COSPAR, ERSI, SCOSTEP, ERSI in Commission G. He is also international expert for the usage of AMU radar, the Equatorial Atmospheric Radar Advisory Committee, Kyoto University, and many other organizations in India. And as I said, he has guided various students for their doctoral degrees, and he has published more than 132 scientific publications. So with these words, I would like to invite Dr. Amit. He'll be talking on a very important topic today, highlighting why the equatorial ionospheric study is important, especially from the point of view of the navigation and communication applications. So welcome, Dr. Patra.
Thank you, Dr. Pant, and also the co-chair, Dr. Jagadheesha, for giving me this opportunity to speak to all of you and share the kind of research that are going on in the country, with special emphasis on navigation communication applications that are coming up in our country, especially in the context of NAVIC. So the title that I have chosen is Equatorial Ionospheric Research Relevant to Navigation Communication Application, Current Status and Way Forward. I have a problem now. It's not progressing. Okay. So am I audible, Tarun?
Yes, yeah,
okay.
You're audible.
Okay.
Your slide is
no.
in the... Yes.
Now it is going, I think.
Yeah.
Is it going now?
Not yet.
Not yet?
No.
I see. So it's a very classical
Seem
problem.
to have stuck, actually.
I have, see, this is the first slide. Then I have moved to the second slide.
May I interrupt? It typically happens when you're sharing the screen, you don't share the full desktop, which is screen 1, and share only one particular window. Maybe you should stop sharing.
Now it's moving, and you can put it in the full screen mode, probably.
Okay. Yeah, I was afraid about this.
If you share and begin with the desktop sharing mode, which is screen 1, you should not face that.
Now is it okay? Should I do? Can you see the second slide now?
Yes, we can. Can you go?
Yeah,
please?
we can see the second slide. Yes.
Okay, then I think it's fine. So I'll just make a move forward. Is okay?
It's actually still in the... it's not in the full screen mode. If you could do it, that will be great.
Full screen. It is here full screen. Can you do this one?
I think as Dr. Dibyendu was telling, it's probably you have to share the full screen.
Can you please stop sharing? Go out of the sharing mode.
Yeah.
Okay. Now click on the share button again. You will see various options. Choose the leftmost option, which is the desktop screen 1.
Okay. Okay.
Now go to full screen mode.
Screen, where is the full screen? Here. Oh, here. No, it's not.
Yeah. Now move back and forth once.
Now it's fine.
Move back and forth once. It is not yet confirmed. Move back and forth. Okay. Now you're confirmed and you're good to go. Thanks.
This is the second slide. This is the third slide. Is it okay?
Yes, absolutely fine.
Oh, nice. Thank you very much. Amit. It's not moving here. Can you do this? No. Okay. So the outline of my talk is I will give a brief introduction to the Equatorial Ionosphere and the communication navigation issues. And two topics actually I will be covering on the Equatorial Ionosphere. One is on the electrodynamics, electron density and tech variabilities, the kind of research that are going on. And also the equatorial plasma bubble, the physics and forecasting issues. And finally, briefly, the way forward. So when we talk about the Equatorial Ionosphere, this is a very familiar, the picture about the Equatorial Ionosphere. We have on the x-axis the latitude, y-axis is the height, and at different local time, if you see the electron density, you can see the anomaly. And that's a very important phenomena that occurs over the equatorial zone. So the Equatorial Ionosphere is highly variable with local time, season, and solar activity, as well as longitude And not only this, that the equatorial ionosphere is very dynamic, not only because of the production, because it receives the maximum energy from the sun, and also the complicated electrodynamics it has. So because of that, the variability is very large in the equatorial ionosphere. And finally, in the evening, the equatorial ionosphere actually becomes disturbed, and it causes a lot of disruption to the communication navigation issues through what is so-called the equatorial plasma bubble. And that is the one which is actually keeping us busy all the time, whether we are in a position to predict the equatorial ionosphere. So this is the issue. Now, as far as the ionosphere and radio propagation is concerned, because we are talking about navigation and communication, so we talk about the radio wave propagation. So it reflects, refracts, diffracts, and scatter radio wave, depending upon the frequency, density, and gradients. And also in the evening, the plasma bubble, that basically when the instability grows in the equatorial ionosphere, so they form what is called as equatorial plasma bubble. And these are actually the density depletions. They are not just simply density depletion, but they also accompany the plasma irregularities of very large scale sizes, through which, when the radio wave passes, then it undergoes amplitude scintillation and phase scintillation. So in a way, the equatorial ionosphere is both during the stable and unstable state is highly dynamic. Now, when we talk about we are already familiar with all these constellations, the GPS, GLONASS, Galileo, BeiDou, and also we have our own navigation system called NAVIC, which is basically a regional constellation. It currently operates 7 satellites, and then it addresses about our own region, focusing over India and also the adjacent areas of centering around India. So this is for navigation. So if you look at the other constellation, so this particular constellation, the orbits, they are very, very unique. So it is actually, this itself is quite interesting as to how this unique constellation can be used for navigation, and how this particular unique constellation can be used for learning the equatorial ionospheric process, which can then be used for the navigation correction. So this is something which need to be really looked into very closely. Now, when we talk about the ionosphere and the satellite navigation, the parameter of ionosphere that produces most of the effects on radio signal is basically the total electron content. So what is the total electron content? It is the total number of electrons integrated between 2 points along a tube of 1 meter square cross section. So this is not per meter, that's why not per meter cube, but per meter square. And 1 Tech unit is equal to 10 to the power 16 electron per meter square. So these are the numbers which we often use. Now, as far as the GPS navigation we talk about, the satellite signal comes to the ground. But if you have the intervening medium, which is full of electrons, then you have the total electron content. Then in the equatorial region, you can get some ballpark figure what kind of actual effect will be there. Basically, the ionosphere delays the signal, and the kind of delay that you can come across, for example, in the equatorial anomaly crest region, which has the maximum electron density, you get about 40-meter delay. And as a function of local time, if you look at, so this varies from about 10 meter to about 40 meter in a slant path during the solar maximum condition. In the solar minimum condition, this comes out to be about 15 meter. So this is the kind of error that you will come across. This implies that if you are going to land from the space, so before you land for about 40 meter above, actually you will have a hard touch on the ground before you actually land. I mean, as per your information, that's the 40 meter, that is what it means practically. So it is going to be a hit on the ground, not a smooth landing, if you are not taking care about this particular error. So this is not the only thing that the ionosphere does. When the ionosphere becomes unstable, it generates plasma irregularities. Plasma irregularities, particularly what we call as the plasma bubble, which is a very large scale plasma depletion. And you often come across that your ground receiver is become actually out of lock. And you can see that vertical in this figure, the vertical bars are actually representing the how many times on a given evening your receiver can be out of lock. So essentially that means this bubble can cause disruption in communication of the satellite signal. They can cause amplitude and phase scintillation, which implies that your signal bandwidth can be severely restricted. So this is the kind of effect that we will see. And any day when you talk about the GPS receiver, any station close to the anomaly, especially, so you will come across this kind of loss of lock of the receiver and scintillation. When we talk about scintillation, you can have amplitude as well as phase scintillation. And right side figure shows actually the kind of amplitude and phase scintillation that you will come across, for example, at the L1 signal. So these are actually the kind of effects that one will come across when we are going to use the GPS or similar kind of constellation where we are using L1, L5, those kind of frequencies, L-band frequencies essentially. So now what I will do is I will come to some research which are actually going in the country as well as worldwide, and where we stand today as far as our navigation communication issues are concerned. So the equatorial ionosphere, the first part is the equatorial electrodynamics, electron density and tech variabilities. We'll be covering both observation and modeling and the current stage. So the vertical plasma drift, which actually plays a very, very important role. This is basically driven by the electrodynamics, and the electrodynamics is driven by the neutral wind. And so this electrodynamics is so complex and so variable that the ionosphere is primarily, actually I should say primarily decided by the electric field that occurs over the equatorial zone. So there are other factors which also add to it. This is basically the neutral wind. For example, the north-south neutral wind plays a very, very important role in deciding where and how much will be the anomaly crest, where the anomaly crest will be located and what will be its intensity and things like that. But electric field is a very, very important parameter which is used not only to describe the equatorial ionosphere, but also the plasma processes. So when you talk about the satellite observation on the right side, you can see the longitude running on the x-axis and y-axis is the local time. And for different season, if you look at the top one is for the equinox, this is the solstice, both solstice. So you can see that there is a lot of variability as far as the longitude is concerned. This is what we talk about the wave 4 structure. And in around 1900 hours, you can see consistently there is a strong electron density electric field, which is represented by the red, which actually represents the pre-reversal enhancement of the electric field, which itself is a subject of investigation as to how this electric field varies on a day-to-day basis, because it is not just a localized process, but it is along the magnetic field line, the kind of the electrodynamics that work and map. When you come to the summer or the winter, you see a very different process. And that's the reason why actually in the equinox, we often come across the equatorial plasma bubble in the post-sunset hours. And this is precisely the point many people talk about. This is the pre-reversal enhancement of zonal electric field is so important to produce the plasma irregularities, instabilities in the post-sunset hour. On the left-hand side, you have the CNOPS observations, and CNOPS, this blue dots are actually representing the CNOPS model, CNOPS database model, and the other points are representing the Hikamarka observations. So if you compare, actually they do quite good comparison. This indicate that we have fairly good idea about how these electric fields are actually varying as a function of longitude and also at different time. But unfortunately, what happens, any satellite does not give the time history of the electric field. And that is where actually the crux of the problem lies, because it gives only the longitudinal variation electric field at different local time, but you don't have the time history. And this is where any ground observation or any such platform will be able to provide the local time information about the electric field. That's something very, very important for us. Here is where actually the 150 kilometer echoes come to the rescue. The fact that if you want to measure the electric field, you need to have a very powerful radar called incoherent scatter radar, which currently we do not have. The only incoherent scatter radar which is located in the world is at Hikamarka. And that is the one which is used for most of the, model, but with the different satellite coming in, we have a better picture about this wave force structure and also the longitudinal variation in detail. So this is where actually in the Indian sector, we have tried to utilize the so-called daytime 150 kilometer echoes. And this is the drift which is shown at the bottom. The good thing about it is that it does not show the much height variation. So you can just have integration and you get, this is the zonal, this is basically the vertical drift representing the zonal electric field. On the right side, you see there are two dots, red dots, which are actually the synopsis observations on a given day. And you see a very good agreement between the two. And this is the one which have been used for developing the electric field model in the Indian sector. And we have finally extended the same thing to the Indonesian sector. This is basically the measured Doppler velocity have been used for the Indian sector and Indonesian sector through a neural network system and to develop the daytime electric field. And daytime electric fields are important for understanding the equatorial electrodynamics during daytime and so the anomaly development. So these are also extremely important. So the model vertical drift shows beautiful seasonal variation with equinoxial maxima, a feature which is very well known based on the Hikamarka observation. Now, when you compare the synopsis observation with the model that we have developed, you see a very good agreement. There are dispersions, but those dispersions have been examined and those have been found to have due to the latitudinal variation in the synopsis location and also due to non-coincidence of the local time. So, but this is something very, very interesting. If you look at on the left side, the red represents Koto Tabang, that is Indonesian sector, and Gadangki is in the black. And you see on a given day, sometime there is a very good agreement between the two measured velocity. On other day, you can see difference. And then the right side, you see the model output. Both are actually the neural network model, and very nicely, the model is reproducing the kind of difference that we have observed in these two locations. So particularly for this longitude sector, I think this is doing fairly good as far as the vertical drifts are concerned. There is another kind of research which is going on in the country is the modeling the NMF2. This particular modeling is very, very important when we talk about the ground-based communication or for the OTH application. So this is actually again a neural network-based modeling which was done by the IAG group here. And you can see this is the longitude and you can see the anomaly going quite well. And these are the observations and this is showing the local time variation as a function of the latitude. And so this kind of research is going on in NMF2. Actually, my idea, I want to eventually come to the what is called the total electron content variation. When we talk about the total electron content variation using the any of the constellation, then actually it's a large vertical column that we are talking about. And when we talk about FO, F2, or we talk about the bottom side of the F region, we are talking about the local. This is only the F region component. But then much of the variability that we understand that it is basically because of the dynamical behavior of the equatorial ionosphere, maybe confined to about 500 or 600 kilometers. And this is where the digits on the observation, if you look at on a day-to-day basis, there is a considerable variability. And this variability definitely must be part of the total electron content variation as a function of local time. And so is the case with the latitude. So what we have done is that we have made an attempt whether we can reproduce this particular electron density profile, particularly the bottom side of the F region, that is up to the peak electron density, the height of the peak electron density. And I think the neural network is doing beautiful job. And this is on a given day, that 26 February 2016. So this is the model output. And if you look at the observation, I think it is producing fairly good, but this needs to be further fine-tuned with some of these finer variations which are not actually getting represented, especially in the evening hour. And I must mention that evening is extremely dynamic, and this is not only the F region, this is actually controlled by the low latitude region, and this also needs to be actually addressed. So this is actually the target that we should actually arrive so far as the navigation is concerned. This map shows the longitude and latitude at a particular local time, 12 UT. And this is actually observation. So the first one is for a 15 March 2001. This is the high solar condition. This is the low solar condition. And you can see, although the map looks similar, but on the right side you have the scale, the total electron content is about 110 tech unit, whereas for the low solar it is about 32. So roughly 1/3 kind of in the peak. So this is the kind of map which have been generated by some other group. So in our country also, if you look at the kind of effort that many of our colleagues are putting in, is to find out the local time, seasonal and solar activity dependence of the total electron content. This is an example from Gadanki, where the left side shows observations for 2009, and the scale is up to 50 here. And on the right side, this is 2013 for a high solar condition. The scale is up to 100. So you can see again the same thing about 1/3. The maximum take during the low solar is about 1/3. And there is a considerable variability as a function of local time as well as season. This is something which is very, very important. And if we have to understand these variabilities, I think the electrodynamics, the FOF2, then all the bottom side electron density profile, if we merge together, I think it is possible to get a good data-driven model, total electron content model for the Indian longitude, which could be potentially used for navigation corrections. So this is an example which has come out from the effort during the Gagan time. This is the map with geographic longitude and latitude in the Indian sector. And this is coming from the 20 receiver data. So you can understand the potential of the number of receivers producing actually a map. So it is very vivid that you have the anomaly crest here, located here, and then the electron density is actually decreasing on the both sides. So this is the potential. I think this potential has to be tapped with more number of GPS receiver. Now coming to the second part, I will be talking about the physics of plasma bubble and our prediction capability. So when you look at the equatorial ionosphere as a function of local time on a given day, it behaves like this. So the electron density picks up in the afternoon, and then due to the electrodynamics, the F layer goes up to the higher altitude. The bottom side is recombined. You can have the sharp gradient. And these are the structures which generate in the post-sunset hour, which we call the equatorial plasma bubble, and continue to be subject of investigation because of the disruptive effect on the communication navigation issues. So this is in a nutshell. But if you come to the conventional wisdom says that, so when the bottom of this particular panel, if you see, the electric field is varying as a function of day, and then you have the pre-reversal enhancement, which pushes the equatorial ionosphere F region to the higher altitude, and where you have the recombination at the bottom, so it provides the sharp gradient at the bottom side of the F region. By going to the higher altitude, you attain the very low collision frequency, by which you can have a relativistic type of instability. The fact that you have the high density plasma sitting on the top of the low density plasma, it could be unstable if you have a perturbation at the bottom. So that's the key point, that if you have perturbation, it is very likely that it could grow due to the gravity-driven current. And that's the related type of instability that we talk about in the ionospheric case. So historically, it has been found that the occurrence of this equatorial plasma bubble as a function of longitude, and this is the season here on the y-axis, it has a beautiful correlation with the pre-reversal enhancement of zonal electric field. Okay, this is more or less well accepted by many people, and that's how the pre-reversal enhancement of zonal electric field has been used as a precursor, as a possible precursor for equatorial bubble forecasting. But you see there is a fallacy here. See, the growth rate of the relative instability on which we completely depends on is basically driven by a nonlinear term is called G over Ni. So E by B is not nonlinear. Okay, and then when you have the depletion, then it goes proportional to that. So it is surprising that instead of the height, how actually it is getting correlated with the E by B. We have to note that this E by B, this is the vertical drift, it is instantaneous drift, not the time history of the drift. And that is where is the fallacy. So there is an important observation that has come up recently, that while the PRE is found to be statistically correlated with strong irregularities, that the same, because this is the same plot, this is the longitude, and this is the season, and on the top you have the pre-reversal enhancement peak, and at the middle you have the density perturbations which are strong in nature, they are well correlated, I should say fairly correlated, but when you come to the weak density perturbations, they are not at all correlated. This is something very, very surprising and need to be investigated as to how this PRE is related to the strong irregularity, but not related to weak irregularity. That is something very, very fascinating. Not only that, the pre-reversal enhancement, more or less, we know that occurs in the evening hour. That means the time is nearly fixed. But what is happening? What is the prehistory before the peak coming in? And also, what are the type of variabilities? So this means that not only this is the local time, this is the day number, this is the day-to-day variability, but this day-to-day variability must be mixed with the longitudinal variability that we see through the observation from a fixed station. So this is something that needs to be looked at, because this longitudinal variability in the pre-reversal enhancement possibly decides as to when and where these plasma bubbles will be seen or they will grow. So the other relevant facts is the plasma bubbles are not only formed at the magnetic equator, but they do extend in altitude and latitude as they evolve. And their occurrence varies remarkably on a day-to-day basis. This is something very, very important. The height and latitudinal extension also vary remarkably on a day-to-day basis. So the evolution, I think, is the most important thing as to up to what latitude this kind of disruption or the effects of plasma bubble will be seen. So plasma bubble also evolve while extending to higher height and latitude. This is that means if a particular plasma bubble we see at the equator, its basic morphology could be one type, but as it goes up and then also map along the magnetic field line, and if you observe along the magnetic field line, so its morphology could be very different. So that is something that we have to keep in mind. So this is an example of 630 nanometer irregular depletion, which comes from about 250 kilometer altitude, representing the latitudinal mapping of plasma bubble along the magnetic field line. So, but the bubble, as I mentioned just before, that they just don't map actually passively, as they actually map along the magnetic field line. So they also encounter different density, and obviously they will have the changes, the evolution as they move. So that is something very, very important. So here is an example. So this is where we talk about nonlinear growth, we talk about bifurcation, we talk about pinch up of plasma bubble. So here is this is a simulation. So you can see that low density plasma actually with time is growing and growing in altitude. As it grows in altitude, you can see the bifurcation taking place. The question is that why this bifurcation is taking place as it moves up. This is actually in a plane, longitude and height. So when you, and then finally when this bifurcation takes place, there is a particular state, one of the bubbles will get pinch off from the mother bubble, and then it will be more or less like a fossil because it does not get the energy from the bottom. So it will survive for some time and then it will go into the decay mode. So this kind of bubble, this pinch off bubble, will actually have a different kind of characteristics in terms of their scintillation or whatever you call it. Again, I'm stuck. Okay, so when we talk about the mapping, actually many times we do a mistake that when we talk about the vertical elongation of the bubble, and then we just simply map along the magnetic field line, but the bubble actually don't map actually passively along the magnetic field line, because as it moves along the magnetic field line, map along the magnetic field line, it encounters a different actually density. And once it encounters different density, so it encounters different resistivity, and that's how the bubble feature will keep on changing. That means what we see over the equator as a function of height, that will not be seen as a function of latitude. This is something that I was just mentioning. Not able to move forward. Okay, so this is a bright example about that. This is an experiment conducted from Seetha in Japan and Darwin in Australia. This is basically the conjugate point, and you can see this is again the 630 nanometer rear glow from Seetha, and this is from Darwin. And you can see that there is a broad correspondence between the depletion channels that have been observed from the northern hemisphere and southern hemisphere, but there is considerable amount of difference. So that means that while they map which actually is consistent with our basic understanding, when they map along the field line in the northern and southern hemisphere, there could be considerable amount of differences in their structures and morphology. So now the thing is, what is known and unknown? So our understanding on the formation of plasma bubble and evolution is fairly good. I think the physics is reasonably well understood. The statistical model of plasma bubble occurrence is also fairly good. But what is then challenging is the deterministic prediction of plasma bubble on a given evening. So that means whether we are in a position to do prediction or nowcasting of the bubble, how much time in advance we can predict, and what is the accuracy of the longitude in where the plasma bubble is going to occur. Those are the uncertainties that remain to be addressed. So now, I will bring some of the aspects which actually deals with this particular challenge. The onset conditions. Onset condition, if you go by the relative instability process, you need to have the F layer sufficiently high altitude so that you have the low collision frequency, so that you have the gravity-driven current working, if at all it is going to work. You have to have a seed. The seed is necessary because the relative instability growth rate is so slow, it takes several minutes, several tens of minutes to actually grow. So that's why if you have an initial, it is very likely that the seed can get polarized, and then so it can grow much faster. The seed will, when the seed is growing, so there is something we call about the upwelling physics, so that I will talk about. Then the prediction, to what extent we are successful, is there anything that we can do but not done? So these are the issues I'll talk. So when you talk about the onset condition, there are three panels. These observations come from the Altair from Kwajalein, which is close to equator. And this is an incoherent scatter radar, terribly powerful incoherent scatter radar. And you can see that the bottom side, you have a very sharp gradient. Suddenly you see that there is no electron density, nearly no electron density. And you have a small perturbations on the bottom of the F region. And with time, this perturbation has grown. And then in the subsequent frame, you see the bubble have already shoot up. That means the bubble growth time is not very long. So this is very, very important. So if you go by the relative instability, it is supposed to take much longer time than what is shown here. So that means there is some process which must be accelerating the process. And this is where we have to bring about the seeding. And I think it is not difficult to appreciate that there is a seed which is working here in the data itself. Then comes is the upwelling. So the question is that if you have a noise like seed, whether this seed need to grow to some level, then only the relative instability will take over. So there is enough indication from Altair radar that indeed at the bottom, and this is what is called upwelling. Because if you happen to be here, just beneath this, you are making the observation, this particular isodensity contour will be moving with a much faster velocity than the adjacent longitude. So this is where, if you are measuring the velocity, this velocity is going to be very large, and contradicts with the notion that it is linked with pre-reversal enhancement. I must also point out here that when we talk about the pre-reversal enhancement, this is a large-scale process, nearly about 30-degree longitude. So this means about 30-degree longitude means about 3,000 kilometers in space. So in that, the pre-reversal enhancement is not going to be very different. So this implies that if you make measurement at a given location, this must be applicable to other location as well, but this is not true. So when you make observation from a given location, that possibly is true for that location and not possible for other location, because there is something else is getting added to the pre-reversal enhancement. That is where we talk about the upwelling. We also should remember that this is not just simply the gravity wave. This is the amplified version of possibly the gravity wave, which is working at the bottom and then leading to the plasma bubble at a later stage. And this is what is the upwelling. Now, when we talk about the seed structures, so here is an exercise that on the left side, these observations are from Gadanki, and this is the decision observation. The decision observations are made from different places in our country. And you can see this is the bottom side of layer, which is going up, and you have the perturbations. You can see the wave structures. From this, you can get the vertical wavelength, use the distillation, get the horizontal. And if you have the scanning observations from the Gadanki ionospheric radar interferometer, which works at 30 megahertz, you will be able to tell about the spacing of the bubble. And when you relate these two, there's the wave-like variations, the horizontal wavelength at the bottom side, and the plasma bubble spacing using the scanning radar observations from Giri, and you find a beautiful correlation. So interbubble spacing and horizontal wavelength observed from decision are well correlated. This actually supports the hypothesis that there must be some kind of seeding is going on. We addressed, but these are the seed perturbation in the electron density. And these density, if they get polarized, it is very likely they could give rise to plasma bubble. But the story, the half story which I have not told is that whether always these perturbations lead to plasma bubble? No. Whenever we have this kind of perturbations, we have also occasion when plasma bubble are not there. That means the question need to address that when we talk about the temporal variation, these temporal variations are only giving the temporal variations. They don't give the direction. So what is important is that what will get polarized, it is the north-south actually is the wavefront which will get polarized. So we have to have a north-south oriented waves. They will get polarized by the horizontal motion. Then only it will happen. So the horizontal, so the direction is very, very important. So if the direction is matching, that is likely that will get polarized. And once they get polarized, it is likely that it could grow to bubble, provided the F layer has gone to reasonable height. The another important thing is, which is also important, that the vertical phase progression should not be too large, because if they move so fast, then where is the time for interaction with the background ionosphere? So the plasma should have interaction with the wave, then only so the interaction time should be sufficient enough. That means the structure should not move too much vertically, so that their phase remain intact. I think there is a good satellite observations that shows that indeed there are large-scale wave structures and upwelling, and those upwelling are the region where you have the plasma irregularities. So this is the electron density prior to plasma bubble, and when plasma bubble is occurring. So this is another finding, that to what extent we can go to the prediction. So what is done here, that the Gadanki ionospheric radar interferometer, which can be used for scanning the east-west sky. So you can see the longitudinal distribution of the irregularities, and when you cut at a particular height, so you can see from where actually the irregularities are generated and then propagating towards east. So y-axis here is the zonal dimension and x-axis is the time. So you can see there are several bubbles which are propagating in the eastward direction, and there is a interbubble separation. So you get information about interbubble separation, you get to know about the zonal motion, you get to know about the location at which the bubble have generated. For example, in this case, the first bubble is generated close to Gadanki, whereas the second one is coming from the west, third, fourth, fifth, all are coming from the west. Unfortunately, it is very difficult to get the eastern side of Gadanki because all those bubbles will be migrating towards east and they will not be captured by the radar. So all the bubbles, however, are very, very important. What this tells us, it tells us about the location of bubble at origin. This is very, very important because if you want to know that whether the background parameters are really indicating the forecasting capability, it is important to know where the bubble is generated. But then all the bubbles are equally important for our navigation applications because the satellite signal has to pass through them. So this is very important.
You have 5 minutes to,
I'll do that. So now, this is a very important finding. This is an experimental proof demonstrating the occurrence of plasma bubble coinciding with the solar terminator, the E region. So this implies that F region is still sunlit. It's still sunlit, but the question is that how much sunlit? What is its effect in terms of the F region parameters, not just physical sunlit or sunset. But what is found here that actually the early time that you will be able to see the bubble will coincide with the E region sunset terminator. This implies that the E region become open, you do not have the conductivity, for example, then any perturbation that is growing at the F region is likely to grow as long as the E region is non-conducting. And that's what is the message that it gives. But on a day-to-day basis, you can see the arrow indicates on a day-to-day basis what are the kind of changes, the temporal, the onset time, the change of onset time. And you see there is a considerable amount of onset time, about 30 minutes, 20 to 30 minutes difference. And this onset time could be attributed to basically the partial short circuiting by the E region, could be. So this is something that has to be investigated. This is about the time. What about the location? When you talk about the plasma bubble, the day-to-day variability about its origin, you can see this arrow indicates that the day one, it is here about 2,000 kilometers west of Gadanki. On the next day, it is right over Gadanki. So you can see many, many cases where the bubble is occurring overhead, and the next day it is occurring 1,500 or 2,000 kilometers west of Gadanki. This is something we have to keep in mind when we talk about prediction. And finally, what actually in the growth rate, in the linear growth rate, which we can do simply based on the height of the F layer, the gradient at the bottom, and also the E cross B drift just during the sunset time. So you can easily calculate the gamma, that is the growth rate, and you find that all those bubbles which are in a longitude zone of plus minus 1 degree, or you can say plus minus 120 kilometer roughly, they can be easily predicted because they are giving growth rate higher. As you actually come to those bubbles which are away from Gadanki, when you use the parameters from decision day observations from Gadanki, they are not applicable for those bubbles because the conditions at those locations must be very, very different from Gadanki. And that's why the prediction from one location is going to be difficult. So this is what is the local growth rate instability when you compute, and you come to a confusing state that when the gamma is greater than, this is a number 11 into 10 to the power minus 4 per second for all EPB cases. But when you talk about EPB and non-EPB cases with gamma less than that, actually that is applicable for both EPB and non-EPB cases, which is quite confusing. So we wanted to look at this, that why such confusion is happening, whether we can resolve this issue. And with backtracing information, which I just mentioned, and you come to the conclusion that about 120 to 150 kilometer east-west direction, all your observations from decision day can be used for a faithful forecasting of plasma bubble overhead. But those which are occurring away from this plus minus 120 kilometer, that is plus minus about 1 degree longitude, I think they cannot be predicted from this. So this is the message. And so the way forward is, I just want to leave these two messages. For navigation, I think a national level GPS, GNSS, Navic receiver network is required to generate tech model. And at this moment, what comes to my mind is that the cooperative research among active scientists and institute could be an immediate step forward. And some discussion is going on among the colleagues to join hands to see to what extent we can resolve this problem. I think this is the immediate thing that should be done. And along with this, all other observations and model can be put together to develop a data-driven model. Today we are talking about machine learning and artificial intelligence technique. So all these things can be brought in, and then I think we can have a tech model representing latitude, longitude, local time, season, etc. And then coming to the plasma bubble, that comes to my mind actually is the bottom side, the structures, I think that are very, very important. So imaging the longitudinal structure of bottom side electron density profile, I think is the need of the hour as to where and when the plasma bubble is going to be triggered. So establishment of a HF sounder, which is doable with a longitudinal chain of receiver, would be a possible solution in addressing the longitudinal variation or the image of the bottom side, which will be a feature added to the pre-reversal enhancement of zonal electric field or the height, and that will add to our understanding. Thank you.
Thank you. Thank you very much, Dr. Amit, for this very elucidating talk. So now we are open for questions. I can see that there is a question from Dr. Debyendu. He's asking that there is a dearth of dynamic MHD and kinetic particle in a cell modeling of the global magnetosphere, ionosphere coupling in India. Such models may allow deterministic predictions of top-down forcing of the ionosphere. Do you feel this is a direction which we should develop capability in?
Yeah, I think I would say that equatorial ionosphere should be viewed as a natural laboratory, whether we have, I think he's talking about the disturbance most of the time, the magnetic storm or things like that, which is coming through the magnetosphere. But I think the equatorial ionosphere in the quiet condition itself is very much conducive for the convective storm such as equatorial plasma bubble. I think this is one aspect, but then that cannot be also isolated. There are occasions when those perturbations will map to the equatorial location, and this will definitely change the electrodynamics, electron density, everything together, and it will be totally a different game together. But I think this is also equally important. That has to be combined with the background story, what I just mentioned.
Yeah. I also have a question. Actually, you have already addressed to it in part. That is do you think that our ground-based instrumentation for or experimental setup in India that we have today is enough to kind of address this? And if we can add a few more components to that, what would that be?
Yeah, I think I will say that what setup we have, I won't say that it is sufficient, but I will say that it is nearly maybe 80–90% sufficient. But what is actually missing is that the last slide, that the cooperative research among the active scientists and the institutes, because ionosphere is a distributed target, latitude, longitude, and those things. So once we actually pull all the things, these two issues, I think, can be addressed much more efficiently. But in the second thing, when we talk about the plasma bubble, I think we are not well equipped. I think we need to have some ground observations. One I have suggested, which could be the HF actually imaging of the bottom side with a couple of frequencies. So you get the bottom side. So you have to take care of the refraction. You have to take care of the inversion, so that you get the image, because you are receiving signal, by longitudinal chain of receivers.
Yeah, and probably a better complementarity in terms of the experimentation and on satellite and ground based.
Yeah, I'm sure about this. The two satellites that we have in the plan, I think that is going to be very, very important in understanding the processes, and also to develop some kind of morphological picture in the Indian scenario more closely.
Yeah, we'll take one more question. That is from Dr. Suvan Saha. What will be the difference in seeding strength in terms of gravity waves, polarization electric field as compared to low and high solar fluxes? And also for ion neutral collision frequency as a growth rate factor.
I would say that the F layer should, these are all competing processes because we should not handle one particular parameter at a time. Because if you look at the growth rate, if you see, you have the electric field, you have the G over nu ion, which talks about the height of the F layer, and you have also the gradient at the bottom side. This is the basic thing. But then when you calculate the growth rate, you come to a point where you see that it is taking too long time. This is where we talk about the seed. But the question is, when we talk about gravity wave, I think gravity waves are omnipresent in the ionosphere. That's my understanding. The question is that all gravity waves will not seed. So we need those gravity waves which are actually east-west aligned. That means their phase fronts are aligned in the north-south, so that when the wind blows or the whatever blows along those things, so they will start getting polarized. So this special orientation, I think, is very important, particularly at the equator. Otherwise, things will not grow. Even if it is tilted, for example, let us say you have a depletion at the equator, but on the northern side, you will have enhancement. On the southern side, you can have enhancement. So it will not allow that perturbation to grow. It will get sorted out. So we need actually, I should not say perfect, but close alignment with the magnetic field, this phase front. Once it grows, and I think this is where we talk about the upwelling. This is where the polarization process comes in. And once you have the polarization process, you have everything for the related instability to take over, provided that the gravity-driven current is, that system is working. That is the related truly.
Yeah. Thank you. Thank you, Dr. Amit, for this accelerating discussion. So now it's my pleasure to invite the next distinguished speaker for today, Dr. Prakash Chauhan. I'll request Dr. Patra to...
Yeah, I'll do that.
Yeah. And Dr. Prakash Chauhan, welcome Dr. Prakash Chauhan for this session. So I'll just introduce Dr. Prakash Chauhan. He is at the helm of affairs at Indian Institute of Remote Sensing, Dehradun. He's also the director for the Center of Space Science and Technology Education for Asia and the Pacific, which is a UN affiliate organization. Those of us who know him very well, he is an alumni of IIT Roorkee. He obtained his doctorate in physics from Gujarat University. Before coming to IIRS, he was in Space Application Center. He was heading a group there. And I must say that he was the person who initiated the research there in the area of Earth observation applications, especially from the point of view of remote sensing technology of natural resource management for oceans and land resources. And also the study of solar system objects like Earth's moon and Mars through Indian planetary missions. He has done a tremendous amount of work in the hyperspectral data for lunar surface composition mapping using our own high sea and moon mineralogical mapper M3, which was on board Chandrayaan-1. He was also the PI of infrared imaging spectrometer, which is on board the Chandrayaan-2 mission. He has published more than 100 research papers in international journals. And also, he is a member of many international and national organizations. He is an executive member of International Ocean Color Coordination Group. He is representing ISRO in that. He is currently a member of NASA ISRO Planetary Science Working Group. He has been awarded for his contributions by various agencies, namely Professor P.R. Pisharati Memorial Award, Hariom Ashram Predit, Dr. Vikram Sarabhai Research Award, ISRO Merit Award, and Satish Dhawan Award by various institutions. So with these words, I invite you, Dr. Prakash Chauhan, to deliver your talk. The talk he's delivering today is very interesting because all of us know that no, moon is bone dry, but then I think he's going to tell us that no, it is hydrated. So, Dr. Prakash Chauhan.
Thank you, Dr. Pant, for the introduction. And first of all, thank you very much to the organizers of Space Science Symposium 2022 for inviting me to give this talk on a very interesting topic, which is on the hydrated moon, which I'm going to talk about because a lot of things in the previous talks you heard about our planetary missions, and I am going to focus mainly on our the findings of both Chandrayaan-1, Chandrayaan-2, and some of the international findings, where the view about the moon is changing dramatically, and we will go through a journey of almost 4 to 5 years of research, which has really brought out this new view about the moon, that from bone dry or absolutely dry, how things have been changing as the new findings are coming up. So I hope you are able to see my slides. Tarun,
yeah, we can.
Yeah, sure. So as all of you are aware, we are living in this solar system, and the closest one to us is, of course, our own planet, and we have this Earth-Moon beautiful system. So this is a beautiful image which has been captured by one of the satellites, where you can visualize both Earth as well as the moon going around it. And you can really see the contrast in terms of a blue planet, which essentially is a water planet, and its own natural satellite, where you see the backside of the moon going around the Earth appears to be of totally different color and different shades. And these contrasting differences between Earth and moon are because of various regions, as many of you are aware. We have a thick atmosphere around us, which also gives us mild greenhouse gas effects, and then it is able to sustain a good temperature on the surface, and of course the pressure which is there due to the atmosphere also is conducive enough to have water in all three forms. However, on moon, similar such kind of situations are not there, and the surface temperature varies dramatically from lunar day to the lunar nights, as well as there is no presence of atmosphere around the moon. So essentially the presence of liquid water has been ruled out, and of course now, as we understand, there appears to be some water ice deposited in what we call as the permanently shadowed regions in the polar regions of the moon. So the basic quest why people are thinking and studying moon is essentially going around these 4 or 5 basic science questions. People want to understand how did the moon formed, what has been happening since its formation, and then there are a lot of mythical things are also there about the lunar surfaces. Of course, many lunar exploration missions have changed that perception, and of course now in the current era there is a race for understanding about the lunar resources, and also to map and maybe in times to come to exploit these lunar resources for various aspects. So keeping these 4 or 5 central points in the mind, large amount of lunar missions have been there by various space agencies. In fact, with the Apollo program of United States of America, when they put the humans on the moon itself, the race for the moon really hotted up. And as we speak, major space agencies have put either orbiters, landers, and of course the humans have also landed on moon. So we have Russian programs, American programs, Chinese, Japanese, Europeans are also into this race, and the last entrant was Israelis. And of course, India, as you can see, we have put 2 missions, Chandrayaan-1 and Chandrayaan-2. And of course, there are a lot of amount of landers, and the landing events also has happened onto the moon surface. As far as India's journey to the lunar exploration is concerned, we have now very effective presence from the low Earth orbit to geostationary orbits around 36,000 kilometers from the surface of Earth, as well as to a distance of around, average distance to moon is around 385,000 kilometers. And of course, you heard about our Mars mission as well. So as far as the moon is concerned, in 2008, we launched this Chandrayaan-1 mission. And in the previous talks, you heard about the various scientific findings from various instruments which were there on the Chandrayaan-1 mission. And of course, in 2019, onwards, our Chandrayaan-2 orbiter is going around the moon and providing large amount of data about the lunar surface in different part of electromagnetic spectrum. Now, as far as the lunar science concepts are concerned, people are more interested to know about the composition of the moon surface. They want to know what kind of minerals are present on the lunar surface. Then, of course, there are different type of, experiments which has been designed to understand these issues. But another important aspect is the presence of water onto the moon surface, as well as in its very thin exosphere. So all these drivers or the scientific issues are driving the quest for the moon. I will not go into details of each of them, but specifically talking about the water on the moon, it all started when people were basically using telescopes and other ground-based observation systems when they were trying to figure out what type of morphological features are there on moon. And later on, the satellites also confirmed, very conspicuous river-like features on the moon, which you can see over here in this image. And initially, the scientists thought that these are the rivers, like the one you have on the Earth's surface where the liquid water flows. However, later on, this conception was, ruled out because most of this sinusoidal features or the riverine features were the features created because of the lava flows onto the moon surface. Then, of course, along back in 1967 itself, the lunar scientists started talking about the presence of water, but the samples which were brought by the Apollo mission astronauts, when people analyzed the geochemically these samples, they found that most of these samples were not showing up any trace of water. Whatever small amount of water was supposed to be detected, it was thought to be the contamination while these samples was transported from the lunar surface to the Earth. However, by the time, the much advanced techniques for analyzing these samples were introduced, so this view about the bone dry moon started changing to a moon which is what we can call as the damp moon. That means people started seeing, a very, very trace amount of water, around 50 ppm or so, in these pyroclastic glass beads. There was a paper by Saul et al. Where they analyzed these glass beads from the return samples and found that the concentration of H2O and other volatiles decreased from the center of the beads to the edges, indicating that there were lost in the surroundings of the tenuous temporary volcanic atmosphere which erupted the magma, and then basically the trapped water was supposed to be coming out of the lunar interior. Subsequently, there were large amount of remote sensing based observations which were, there in different missions, and I will talk about them in the subsequent slides. But it is also important to know that how the water is being delivered and what kind of water cycle you can expect on the moon surface. So it is believed that the water was, delivered to moon by comets, by the asteroidal impacts, by interplanetary dust particles, by the giant molecular clouds from the, from the galactic systems. And of course, there is also a continuous process by solar wind interaction onto the lunar rocks, which also produces, the water molecules as well as the hydroxyl ions, and then there of course is a transportation process which we'll talk about later on. And then of course moon itself produces some amount of these water molecules through degassing and by other processes. So as we speak today, scientists are getting to put together the X together, and then they are thinking that maybe a very, very tenuous water cycle basically is active on the moon surface in terms of solar hydrogen implantations during the sunlit side, and then the moon also has contrasting surface temperatures from the day side to the night side. There is a good amount of transport also takes place, and then some of this water can also get leaked through the very tenuous exosphere, and of course through the degassing processes, some of these volatiles can also get released to the exosphere. So this is a new field which is getting developed. In fact, we need to understand a lot of these boxes. The clarity about many of these processes still is not there, and that's why large amount of observations are currently being done and being planned as far as the futures of the lunar exploration is concerned. Now, there are another interesting place on the moon. These are the poles of the moon, both the North Pole and the South Pole. Because the moon has very low obliquity, it has a axis tilt of around 1.6 degree or so. So some of these polar regions, or what we call as the permanently shadowed region, which I'm showing you here in the red color, they never receive the sunlight, and they become the ideal places to host some of this transported water molecules over millions of years of time. Now scientists believe that these reservoirs have these water molecules in the form of the subsurface or subsurface water ice. And if you look at the topography of these polar regions also, so these dark areas, you can see there are larger depressions, and then some of these very dark regions, they never receive the sunlight over millions of years of time period. So here I show you a satellite picture of lunar South Pole. So you can see these dark areas, what we call as the permanently shadowed regions, and the recent experiments by instruments like Diviner, which was a NASA mission. They have done the mapping, the temperature mapping of these North Pole and South Pole regions, and they found that the polar regions, especially these permanently shadowed regions, they have extremely low temperatures going as low as around 50 Kelvin, below 50 Kelvin or so. So these are basically the cold trap regions on the lunar surface of the moon. And what I show you over here, a very beautiful animation at the South Pole of moon, where you can see how the shadows moves during the over a large period of time. And even through a complete solar cycle, some of these regions, they never receive the sunlight, and these type of areas, they become very interesting place to find the presence of water. So this type of temperature variability basically leads to what we call as the transportation of water molecules through a process of what we call as the ballistic random walk process, and some of these molecules may be getting deposited to these cold traps both in the north and the south polar region of the moon. So these becomes the ideal sites for hunting water and water ice, and that's why a lot of remote sensing missions are being done to map these resources onto the moon surface. So as far as if we talk of the different techniques which try to exploit the different part of electromagnetic spectrum as far as the lunar water detection is concerned, so we have the exospheric water vapor. In previous talks, we talked about the moon impact probe, and then there are some in situ detection methods by putting mass spectrometers or so. Surface water ice, which is a very important aspect of where you can have large scale mapping, then techniques like infrared spectrometry, as well as for subsurface water ice detection, you need to have longer wavelengths. So you go into the microwave part of electromagnetic spectrum, and instruments like synthetic aperture radars in different frequencies are now being flown. We have currently on Chandrayaan-2 dual frequency synthetic aperture radar, which has L and S wavelengths, where the L band has larger penetration compared to the S band. And then, of course, if you want to know the interior or the trapped water, at certain locations, you still can get some signatures from the spectrometric data. However, the return sample analysis with advanced techniques is also providing an important clue about the trapped water in the interiors of the moon surface. So I'll just take you around to this journey which started almost from these remote sensing missions. There was a mission called Clementine. It was a NASA mission which was launched in 1994. And then, of course, the Lunar Prospector mission, which provided the early evidences of water on the lunar poles. So the Clementine mission, using the bistatic radar experiments as well as this Lunar Prospector mission, they did the neutron flux mapping through a lunar prospector neutron spectrometer, and they found that there were, of course, the presence of hydrogen, which basically came out through these neutron spectrometers at these polar regions of the moon, both in the North Pole and the South Pole regions. And these locations of the polar hydrogen enhancements were associated with the locations of suspected cold traps, which I talked about. So these white regions are so-called cold traps. So around the vicinity of these cold traps, you see the highly elevated hydrogen enhancement from this early, detection from the hydrogen by the neutron spectrometers. Then, of course, came this a very important mission called the Lunar Reconnaissance Orbiter, or LRO mission by NASA, where they had planned what we call as the impacting experiments. So there was an L-cross, impacting experiment where in the upper stage of the rocket, which was carrying this LRO satellite, was basically allowed to hit onto the moon surface, and the ejecta by this hit was analyzed by this L-cross instruments, and then at a location called Cavius crater, which was basically the L-cross impact site, they analyzed the ejecta plume through the spectroscopic means, and a good amount of evidences about the presence of H2O gases as well as the hydroxyl molecules in this ejecta was found by this so-called L-cross experiment, which also confirmed that there must be some form of water either in the presence of attached hydroxyl ions or the free water, which is present maybe in the form of water ice in this polar region, was of course detected by this L-cross experiments. Then, of course, we come to Chandrayaan-1 era, where we had, during 2008 time, a different suite of experiments covering different part of electromagnetic spectrum. So this is the lunar temperature map derived from the Diviner missions. And then there was a synthetic aperture radar experiment on Chandrayaan-1. So that basically allowed what we call as the detection of the water ice at different craters. So more than 40 permanently shadowed craters were analyzed in the North Pole regions, and of course in the South Pole regions, where anomalous behavior of backscattering by radar signals were observed, and it was attributed because of the presence of subsurface water ice in these polar craters. And of course, then there were certain other experiments were also there. There was another hydrogen detection mission called LEND instrument that also showed that enhanced hydrogens in the polar regions. And then, of course, from Chandrayaan-1 itself, the MIP, the Moon Impact Probe, which basically descended to the lunar surface, also detected water molecules very close to the lunar surface. But more conclusive, and the global presence of water molecules and hydroxyl ions were observed, what is known as another spectrometer on Chandrayaan-1 called the Moon Mineralogy Mapper. This was a NASA JPL instrument which has a spectral range covering from 0.4 to going all the way up to 3 micrometer. And it was basically measuring the reflected light from the lunar surface in this broad spectral region from 0.4 to 3 micrometer. And then the analysis of this data revealed that the polar regions of the moon, both the North Pole as well as the South Polar regions, they showed anomalous behavior in terms of the presence of absorption of light at around 3 micrometers or so. So this 3 micrometer absorption, you can see in this plot that when you are analyzing the polar data, this 3 micrometer absorption was much stronger compared to the equatorial spectrums. And back to back, 2 more papers were published by the flyby missions of Deep Impact Probe and Cassini mission. Of course, at a very coarser spatial resolution, they also showed that at 3 micrometer, they also detected this absorption, which can be attributed either due to the presence of water molecule or hydroxyl ions, which are basically attached to the rocks and the minerals of the moon surface. And a complete, map of this distribution was made and published in 2008, and Chandrayaan-1 was given this credit to first time find the global distribution of water molecules on to the moon surface. However, if we talk about the reflectance spectroscopy technique, so there are 2 major spectral regions which basically are sensitive to the presence of water molecules at ppm level and at 3 micrometer, and there is another spectral channel which is also amenable for detection of water molecules, is around 6 micron or so. So if you look to the reflectance spectra, which is basically recorded by the remote sensing instruments from the moon surface, you will find this characteristic absorption at 3 micron because of the water, or because due to the hydroxyl ions, because the spectral bands are pretty narrow. And then, of course, there is a small absorption hump in the reflected spectra at around 6 micron or so. So if you assume this 3 micron spectra, and if you have sufficient spectral resolution, you will be able to discriminate between the spectra caused by the presence of the water molecules, caused by due to the hydroxyls, and also by the water ice, by making these subtle differences which basically occur in the spectral shifts because of the presence of different phases of the water. So, what was the problem with the M-Cube data is that this particular 3 micron band was very broad, and of course, it was not continuing beyond 3 micron or so. So there, the findings were about water detection, but not very conclusive to provide you information about the type of water and to differentiate between water molecules and the hydroxyl ions which are present on the moon surface. Nonetheless, you saw that polar regions from the M-Cube analysis showed high presence of this hydration feature. However, at non-polar regions, also at discrete locations, some of the researchers, including some of my colleagues at SAC, also found very strong water absorption features at different lithology. So it proved that there appears to be some kind of a geological context or certain type of rocks which has more affinity to contain or to have this hydroxyl or this 3 micron absorption features. In 2018, Shui et al. Also made a direct detection of water ice. So they analyzed this moon mineralogy spectrum and then averaged large amount of spectrums to increase the signal to noise ratio, and detected that some of these permanently shadowed craters in fact have the presence of water ice, which was basically detected using the reflectance spectroscopic techniques. Recently, last year, 2020, there was another interesting news which came out from NASA on the molecular water detection using this 6 micron feature from a ground-based observation system where the spacecraft carried a spectrometer which was supposed to have this 6 micron spectrometer flying on this aircraft, and they looked onto various locations on moon and then recorded this characteristic 6 micron absorption feature. And this 6 micron absorption feature is basically due to the water molecules, unlike the 3 micron where you have presence of water molecules as well as the hydroxyl ion also gives a characteristic signature. So this limited finding from the ground-based observation also confirmed that the water as high as around 400 ppm was basically detected at different locations on the moon using these ground-based experiments. So if we talk about all these findings, one can say that today you have the presence of water and different reservoirs on the moon surface. So you have the polar regions where you have water presence in the water ice form. Then, of course, you have the loosely bound water at different locations, preferably in the polar regions where the lunar rock itself are containing or having this adsorbed water, and with the variability of the sunlight, some of this water is also released in vapor form. And then, of course, you have this mineral bound hydroxyl ions, which are basically also getting detected in 3 micron signal. So you have this, and at certain locations, you have the bounded water, because people have analyzed multi-day data. If you have water present on different time of the lunar day, and if you are not seeing any change in the strength of the water, essentially you can interpret that this may be the water which is bounded to the lunar rocks or to the crystalline structure of the lunar minerals. So such type of water is being termed as juvenile water. Then of course you have the surface water, and then worried water in terms of water ice near to the surface or subsurface in the polar regions. So we had this Chandrayaan-2, a more recent version of a more complex satellite, which was being, conceived, where you had this orbiter, lander, and the rover configuration. Of course, when it came to the payload, definition, then the next question is that whatever detections were done by MQ, how these detections can be improved. So we designed an instrument called Infrared Imaging Spectrometer, IIRS, and then this IIRS instrument was supposed to extend the observations done by this MQ mission, and we designed a spectrometer at the Space Application Center, where we had the spectral range from 0.8 micron going all the way up to 5 microns, so that we can fully characterize this 3 micron absorption feature. So the problem was with the MQ observations, but they were limited up to only 3 microns or so, and some of them were not even complete, going all the way beyond 3 micron. And there was also an issue of what we call as the thermal correction. The moon becomes very warm during the lunar day, and some of these absorption features can get hidden into the thermal emission pattern of the moon surface. So to overcome these ambiguities, which was basically there in the MCube data, this infrared imaging spectrometer instrument was conceived. Here, what I would like to show you that what kind of temperature contrast happens on the moon surface. So you have these warm surfaces during the lunar day. Lunar day is almost equal to 15 Earth day. So the temperatures of the order of around 400 K or so. And lunar nights, you have around, the temperature comes down less than 100 Kelvin or so. So there is a big thermal contrast on the moon surface, and the emission signal from the moon during the sunlit portions is very, very high. It has a strong dependence on the moon, on the temperature. So if for 370 K or so, you have very high emission at around 3 micron or so. So this emission signal also gets merged with the reflective signal, and that is where we need to correct for this emission signal to properly generate your reflectance data, so that you can appropriately characterize these 3 micron absorption features. So this was basically done, and a new instrument, a new spectrometer was conceived, which has this spectral range from 0.78 to 5 micrometers and a spatial resolution of around 80 meters or so. And this was supposed to provide us unambiguous observations about the water and the hydroxyl separability onto the moon surface. So these were the first spectral reflectance data set. This is the radiance information, the reflected energy as observed by this IIRS instrument from different locations on the moon, and you can see that we have a good amount of thermal sensitivity also. So the surfaces which were bright and was having the higher temperatures, you can see the emission is very high, and from the darker surfaces the emission is relatively low. So we started looking into these data sets, and you can see these are few of the early strips in non-polar regions of the moon, of course going all the way up to 60° north, and a good amount of sensitivity from the colder regions to the hotter regions in 4 to 5 micron regions were captured, along with the reflective component in the shorter wavelength regions. So you developed certain algorithms to calculate per pixel temperature on the moon surface, and this temperature, which was inverted from the spectrometer data itself, was used to correct for what we call as the thermal emission effects. And you can see that some of these spectra were corrected for this thermal emissions, and once you correct for these thermal emissions, you start seeing this absorption at around 3 microns or so. So this became basically the basis of detecting this 3 micron absorption feature in continuity or going all the way up to 3.2 micron or so. So remember that MQ observations were only cutting at 3 micron. They were not able to give you the full hydration picture, but now using IIRS data, we are able to characterize these signatures well beyond 3 microns, and we are able to calculate the abundance of water in terms of this band depth of absorption. So here's a picture from a Copernicus crater, central peak of Copernicus crater. This red spectra shows you how deep water absorption is there on this, the central peak regions of the moon surface when you compare to the exterior spectra, which are basically predominantly dominated by the basaltic flows. So these type of observations are now allowing us to generate this two-dimensional distribution of the hydration strength onto the moon surface. And we published a work recently where initial data sets were analyzed, and we showed that how the water is varying onto the moon surface. So basically varying from very small untamed to almost 1000 ppm or so. As you can see over here, over the basaltic mare plains, we don't have the water surfaces, but wherever you have these bright, rocks are called the plagioclase rocks. Many of these rocks forms exhibit a high concentration of water. So it appears so that there is a strong mineralogical control as far as the water abundance on the lunar surface is concerned. And here I show you how at certain locations, even the spectral shift between the water molecules and the hydroxyl ions has also been observed as a function of temperature. So this, more data is now under process, and we are analyzing a large amount of lunar data set. We have already covered almost 90% of the moon surface, and we expect that in times to come, we will be able to give a global picture of water distribution onto the moon surface. This is another, interesting outcome of this work, where you see that in the polar regions now we are able to derive the temperature maps. This is the south pole region of the moon as measured by this our Chandrayaan-2 IIRS data sets. And when I blow up or zoom it up this region, you can start seeing that some of these permanently shadowed craters, they also receive sunlight, and whenever they are illuminated by sunlight, these regions, even though they are very cold, they get some sunlight, and by analyzing the reflectance spectra from these regions, we are supposed to get very interesting results about the volatiles, which may be present in vapor form very close to the moon surface. So this is unpublished result. We are likely to publish this work very soon, where you are seeing how the hydration strength is increasing as we go into the polar regions from the non-polar regions and the lunar poles. Remember the hydrogen strength maps from the neutron spectrometer also showed up. So many of these polar regions really are showing up very, very strong absorption features at our 3 micron spectral region, and these are some of the initial reflectance spectra from the polar regions. There is another instrument on Chandrayaan-2 is dual frequency SAR, which is basically going to look up for the subsurface water ice detection, and my colleagues in ISRO are also working to analyze, and they are getting really interesting data where the ambiguity which is caused by the volume scattering by ice as well as because of the lunar rocks is now being resolved, and they are coming up with a very refined quantitative estimates of subsurface water ice in various parts of the in the polar regions, especially in this permanently shadowed crater region. Another interesting paper which has got recently published last month only, where you may be aware about the China has a very strong lunar program, and Chang'e E5 basically was a lander mission, lander rover mission, and this is basically a lander which is there in the lunar basaltic regions, and then they also have this reflectance spectrometer onto the lander, and this is the reflectance spectra at 3 micron, which has been published now by Chinese group, and it also shows after thermal correction of this spectra, they are seeing the trace amount of water molecules, which is of the order of around 40 to 50 ppm at the volcanic, at these basaltic complexes where the water amount is supposed to be relatively less. So these are very encouraging results, even from the ground-based observations now, we are seeing that, of course, the moon has a good amount of presence of water, of course, not in large amounts, but probably it appears so that the larger areas of the moon has presence of water, may be caused due to the solar wind interaction processes. And of course, what we need to do is now to analyze all these data sets which we have all together. And definitely, if you have to summarize this recent surge in lunar exploration, is basically now hotting up as far as the race for understanding the distribution of lunar resources is concerned. You are already aware about the Artemis program of the United States, where they're planning, to put humans back onto the moon surface. Some of these resources will be very, very useful in terms of sustaining the human presence on the moon surface. And of course, India is also has a very strong, lunar program. We are now going to have a follow-on Chandrayaan-3 mission. China, as I told you, has a very, very strong, already the 5th mission is all on, and Russia is also planning to have another, revived plunge as far as the lunar exploration is concerned. So friends, the race for the moon is really going to hot up, and some of you, especially the youngsters, probably now we have plethora of data, petabytes of lunar surface data from different instruments in different part of electromagnetic spectrum is available and waiting to be analyzed, and new discoveries are yet to come. So I take this opportunity to invite some of you, because ISRO has released this data in public domain, and some of you, those who have interest in lunar exploration, can think of taking this as your career progression. Thank you very much. Thanks for giving this opportunity and listening to me with patience. Thanks a lot.
Thank you. Thank you very much, Dr. Prakash. It was a very, very illustrating talk, journey of this hydration of moon. Very many new ideas. Now I think we are open for questions, and I already see that there is a question from Dr. Dibyendu. Is there any theory that can explain the prevalence of water in the lunar poles? The fact that polar regions receive less solar radiation implies water or ice already there would be preserved, but does not explain how the water molecules got there to begin with.
Yeah, so there are 2-3 ways people are trying to explain it. One is, of course, the delivery of water through earlier cometary impact or so. So if they were delivered in the polar regions, because the temperature is very less, and then some of these regions, what I call permanently shadowed regions, have not seen the sunlight in billions of years, probably that ice which must have been delivered by cometary impact would have been present. That is one way of looking into it. Then, of course, what I call is the solar wind interaction process, where the hydrogen which is being brought by the solar wind interacts with the lunar rocks, and then some of this oxygen is released, and then water molecules or hydroxyl ions must be getting produced by this solar wind interaction process. And the mobility of this molecules from the sunlit portion to the darker or the colder regions, people are trying to talk of this transport process, where over a large geological period of time, this transportation must have created these reservoirs of water molecules. And since the temperatures are very, very low, probably now they are residing in the form of surface or subsurface ice, or even people talk of very, very thin veneer of surface frost, because at that temperature, that's what you expect it to be there. So these are 3-4 type of theories which currently are there. People are also trying to understand the diurnal variability of the water molecules and trying to understand this so-called water cycle on the moon in terms of solar wind interaction. So there are papers where you will see that they analyze the early or the morning reflectance spectrometry data, mid-noon data, and then evening data sets, and they are finding variable signature of hydration strength on the moon surface. So this is a field which is basically really what you can say is just starting to develop. And from our Chandrayaan-2 also mission, we are getting now observations of same place at different time of the lunar day. And definitely we will try to work out and many of you can join this work to understand the the water molecule transportation and water cycle, how the water molecules are getting formed and how they're getting transported and getting deposited into the polar regions. So it's a field which is evolving. Yeah, thank you.
Yeah, there's one more question from Dr. Ramesh. He is asking whether it's possible that Earth could be contributing to the water on Moon. Is there any such transportation possible?
So I did not show up that slide. There is recently using M-Cube data, some scientists have detected the presence of hematite minerals on the polar regions of the Moon. So hematite is produced by the oxidation process, as you may be aware. So the question is that from where the oxygen is coming onto the Moon surface to do this, oxidation. And the spectral signatures were very conclusive. It has been published, and the hematite presence has been shown at various locations. So one of the theory which came out that probably the oxygen is being delivered to the Moon from the Earth itself through the magnetic tail processes. So it may so happen that some of this oxygen which is getting lifted to the higher altitudes probably is also reaching and then doing the oxidation in the polar regions, because the water water in some form is present in the poles, but you need oxygen also, or maybe some oxygen may be also getting degassed. So I think maybe some of the Earth also may be contributing. That's what people are, it has already been hypothesized, and one such publication has already come.
Mm-hmm. There's one more question. It's like the question is, if we compare the rocky surfaces on Earth and on Moon, so from the perspective of water, what can we comment on these two scenarios? Can we infer something from this?
Yeah, so basically, if you compare the the rocks on the Earth and the rocks on the Moon, there is a big difference, because as you know, the rocks on the Moon on the Earth has been subjected to various processes of erosion, and which is caused by different erosion agents like water, wind, and of course plate tectonics has also changed the entire initial crustal structure which was supposed to be there when the primitive Earth formed. However, we still find certain places, especially in the peninsular India, where we find the rocks which are very similar to the rocks which are there on the Moon surfaces, of course, the plagioclase rocks. So scientists are trying to use these rocks as lunar analogs, and then they are also trying to do experiments by using this rocks in the laboratory by doing hydration, and then by exposing them to various experiments, to radiation, etc., to understand and simulate the lunar environment, and to see that how these the water molecules or hydroxyl ions are getting trapped in these so-called the lunar analog rocks on the Earth. Thank you.
There is one more question from Dr. Deepak. He is telling that as there is a wide range of temperature variation in day and night, can we see the changes in alteration products from rocks?
Yeah, so this is also a very interesting thing, of course, I did not talk much about the space weathering process, which is the primary weathering process which occurs on the Moon surface. But the temperature driven, alterations also are leading to the mass wasting events. And of course, at the morning talk, Dr. Anil also showed large amount of boulder mobility and the mass wasting processes. So this mass wasting or the differentiation or breaking of the lunar rocks probably may be happening because of this large amount of temperature variability, because we don't have any other agent which can basically trigger mass wasting on the Moon surface. There is not much of plate tectonics. The lunar quakes have been reported, but they are not very, very strong. So there must be some, or maybe small micro meteoritic impacts which are still happening. They may be causing, but definitely some of this temperature variation must be causing what is also known on Earth, the shattering process or alteration process. Another important aspect is there that in polar regions of the moon, as I told you, the presence of hematite has already been documented. We suspect that there may be some other kind of alteration products may also be seen having different mineralic assemblages because of the presence of now water and of course the delivery of oxygen. So definitely it's a very good question, and we should look for more surprises in times to come if we are able to detect the altered minerals, especially in the lunar polar regions.
Dr. Prakash, I was also curious to know, it's like water, when we take the water and on Earth and see the isotopic ratios like H by D or something, then we find that this ratio has one value. Yeah. And then when we see these ratios in water in different planetary surfaces, they turn out to be different.
Yes.
So what do we have any such information in context of moon?
I'm not aware, because see, this information only can come by the sample returns, experiments. Yeah, because even if you have, because the water molecules, the concentration itself is so low, then detecting, through remote sensing observations, the isotopic composition is almost a very big challenge. So now more and more samples, now you may be aware, Chinese have brought some return samples from that Chang'e E5 mission. But many of them are being, these return samples are the non-polar regions of the moon. In fact, entire Apollo mission return samples also not from the polar region. So wherever you have the high hydration strength, those areas we don't have the return samples from the moon. So probably that's why you will see that in the morning it was talked that JAXA is planning a mission, a landing mission to the polar regions, South Pole regions. So more and more missions now are going to focus on the polar region, and you may see that there may be sample return missions also in times to come, especially from the regions where the hydration strength or the water strength is supposed to be much higher. Probably analysis of these sample returns may give some clues about the isotopic ratios and the composition, which can tell us about the processes which are generating water molecules on the moon surface.
Mm-hmm. Yeah. Thank you so much for patiently answering all these queries, and thank you so much for your very elucidating and interesting talk. So on my behalf and on behalf of Dr. Jagadheesha, my co-chair from ISRO headquarters, I thank both the speakers very much for their interesting and very exhilarating talks today. Now over to LOC.
Thank you all for attending this session, and thanks to all the speakers for these interesting talks. Now the plenary sessions are starting at 2 p.m. So hope to see you all there. Thanks.
Thank you.